Well, hello out there in YouTube land. It's been a little while since I've posted. Um, and the reason is, well, there's multiple reasons, but um, I believe I mentioned in a video or two, my hiking videos, that last year I was living in Grand Junction, Colorado. And I've moved back to Louisville, Kentucky, in an effort to expedite finishing my PhD at the University of Louisville in physics. And of course, as the name implies, my particular concentration is astrophysics, right? Um, and to be quite frank, it took some mental fortitude to make this video. Um, and not so much because of the content that I put together. It did take a day and a half of some pretty vigorous effort. Um, but part of me wants to start leaving the old Earth versus young Earth creationism, science versus religion issues. I think that there are important topics there to cover. Part of me wishes we didn't even have to. I actually think that most scientists who fall into my camp or many of the other debunker camps wish that that were the case. But there's also a little bit of fun that putting these videos and having a teaching moment, right? That might not otherwise come along. For example, talking about creation is a really good way to talk about specific parts of evolution that a biologist content creator might not necessarily think to hit all the time. And that's kind of the motivation behind this video. Um, I will often put these kinds of debates on in the background if I'm, getting ready for bed or something, just to have the noise on. And sometimes a specific thing just jumps out at you, and your brain just goes into overdrive, right? It just goes into overdrive. And that's what happened with this one. And the reason I'm making this video, and I hope not necessarily targeting young Earth creationist arguments ubiquitously with this kind of thought process here, but in any instance where these kind of teaching moments can happen, um, I don't know if this name will catch, but I kind of want to title a series, and maybe this will be the first one in the series. How do we know what we know? How we know what we know? And so I was watching this debate between Hugh Ross and Kent Hovind, and this particular debate took place in the year 2000. Okay, so we're pushing 24 years old for this debate. However, that said, the arguments that Kent Hovind makes are very terrible. In my opinion, both the theological and the scientific arguments are just awful. And this is not unique to myself. Others who have interacted with Kent have often expressed their disdain for his arguments, and even other young Earth creationists don't like his arguments because they're so bad. Okay, they're just bad. And one of the statements that he made, and this is partially why I kind of felt the need to step out of this arena for a while, because it is so easy to go down these rabbit holes. Okay. And so what I'm going to do, okay, we're literally, and I have no idea how long this video is going to be. It could be an hour, it could be 2 hours, it could be 3 hours. It's 4 a.m. on December 1st, so I've got my coffee, and we're just going to chug through this however long it takes. But the reason that I have to be careful with this is because it is so easy to get sucked in and say, oh man, I need to make a video to refute this. I need to make a video to refute this. I need to make a video to refute this. And this, as you can see, this debate, this YouTube video we're going to watch, or the clip from this video we're going to watch, the whole debate is an hour and just shy of an hour and 12 minutes. And the clip we're going to watch is literally 20 seconds long. Okay. And this response from me could take up to 2.5 to 3 hours. Who knows? Okay. So that's why folks in my position have to be very careful, because this can grow into a huge time sink. Now, I think that making these kinds of videos are worthwhile. And hopefully, if you watch this video, you will come away with an understanding of astronomy that you might not have had before, most likely will not have had before, unless you are a professional astronomer, and almost assuredly have some understanding that you haven't had before, unless you have my particular field. Okay, so Kent Hovind is like the low-hanging fruit of creation science. The problem is he's everywhere, right? So when other young Earth creationists, particularly those that have a degree in some scientific field, if not a terminal degree, most of them are staying out of the kinds of debates that Kent Hovind does. The debate platforms like Modern Day Debate or things like that, or going on to other people's personal YouTube channels. But Kent will, right? And so he has far more content, and I think that's by design, because obviously the more content you create, the more nuts you're just going to catch. If you're a squirrel, right? If you're a fisherman with a bigger net, the just more fish are randomly going to swim in, and you're going to catch them. So I think it's by design that he is kind of still out in the internetosphere, talking about these things and promoting his ideas, to keep himself in the I hesitate to say spotlight, but keep his name out there, right? But his arguments are absolutely terrible. Okay, so like I said, this clip, this whole debate is worth watching. Okay, if you have an hour to spare, or if you're washing dishes or doing some menial chore that takes a little time, put the debate on and give it a listen. But what I want to do, and the reason that this video could take a little time, and so I'm going to ask for your attention, but what I want to do is kind of go front to back from the beginning of observational astronomy, from the time when we had cameras and started making observations. How then have those observations progressed, and how has our knowledge progressed to the point where we can make a firm conclusion about this thing that he is saying, okay, about the claim that he's making here, okay? So we're just going to play a few seconds of the debate here, and we'll dive into front to back. Okay, and this touches on my field, which is why I kind of spent a lot of time making the background material for the video, because this is something that I have some expertise in, like this very niche part. And so I kind of wanted to walk through how are we doing modern science right now in this area, and why is it impacting his claim. Okay, so this is not just like a general I'm going to say things, astronomers say this or astronomers say that. I'm going to point you toward primary sources, primary pieces in the literature, and kind of build from the ground up why we think we know what we know about stars. Okay. And hopefully there's invariably going to be things that I leave out. Okay. So if you do have expertise with stars and you say, well, you should have said this or you should have said that, I'm just going to ask for a little bit of grace, because there's absolutely no way I can cover everything there is to cover about stars. But I do want to cover some of the major things that have impacted what we know about stars. And then in my particular field, how we're utilizing that knowledge to make new discoveries, test predictions, and how these relate to the claim that Ken is about to make. So let's go ahead and give it a listen. Now, so just to give a brief minute of context, they're talking about entropy in the universe. So this line of questioning that they're responding to is about entropy in the universe, and whether or not entropy occurred in the universe prior to Adam and Eve eating the fruit. So, of course, if entropy was in the universe before Adam and Eve ate the fruit, then the universe was already starting to run down. Okay, so that's kind of the implication that's going on. All right, so
if the sun is burning, there's two theories about how the sun burns. By gravitational collapse, therefore it's burning up its fuel, and therefore, or the other one is just nuclear fusion. It's just take very little energy, would go a long time.
Okay, so this is why. This is why these videos are dangerous for me. That one little claim is going to take up this entire video. Okay, this one little claim is going to take up this entire video, and again, it could end up running 2+ hours. So grab your coffee, pause the video if you need to from time to time, but I do encourage you to watch, get through the whole thing in some way, if not in one sitting, in chunks, because the end result is going to wrap this up in a nice little bow, or at least I'm going to try to, and show you exactly why this claim is bogus. Okay. Now, so let me preface this with, there had been two competing theories in the past about how the sun shines. Okay. And the reason I'm being very persnickety is because he's using the present tense. He used the present tense. He said the sun shines, right? There are two theories as to why the sun shines. There are not two theories as to why the sun shines, okay? There were, but now we're 99.999999999% confident, actually probably a few more nines in there, confident that we know the answer is nuclear fusion. Okay. And this is what I want to hopefully try and convince you of, right? Now, the sun certainly has experienced gravitational collapse. And it will experience gravitational collapse, particularly in the future. And it's actually experiencing gravitational collapse right now. However, it cannot possibly be experiencing gravitational collapse and only gravitational collapse. Before the nuclear fusion started, when the sun was in its pre-protostar stages, as the gas cloud was condensing and then the protostar was forming, yes, gravitational collapse was by far the dominant thing that was going on then. But as soon as the temperatures and pressures at the central part of that blob were hot enough, when nuclear fusion started, all of a sudden something changes. Okay? Something changes, and gravitational collapse is no longer the predominant energy source. Okay? So we're going to walk through this step by step. And remember, this, even though this video is 24 years old, this was more or less settled well over 50 to 60 years ago. Okay? Even 40 years ago, it was already pretty universally accepted that it was nuclear fusion currently powering the sun, not gravitational collapse. So again, this is why these are dangerous. This one little 15-second clip is going to be a 3-hour response, okay? Or potentially a 3-hour response. Hopefully it's not. But let's go ahead and get started, okay? So how do we know, right? So again, there were the two claims. Why the sun burns, the first claim he made was, or the first theory he said, is that it could be gravitational collapse or it's nuclear fusion. So I'm going to argue that the best evidence is nuclear fusion, and I'm going to do so by going through the history of observational astronomy into my field and arguing that nuclear fusion is by far, and not even close, okay, by far the superior option based on our theories and the evidence that is supporting those theories, okay? So we're going to run through the history of astronomy, and it starts with stellar parallax, and then the HR diagram and energy mechanisms. And this is going to kind of start to get the conversation going on these two ideas, talking about the instability strip on the HR diagram. And so all of this is going to build up into the field of stellar pulsation. Okay, and stellar pulsation is my particular field, and I particularly study a group of stars called Delta Scuti stars. And we will talk about how the pulsation equations and the stellar structure equations are related to each other. Okay, and this is going to be the key. The energy mechanisms are going to be inherently built in to the stellar structure equations. Okay, so when we say we know what's going on inside a star, or we're going to calculate what's going on inside a star, one of the ways to do that is with a set of equations that basically govern the physics in the interiors of stars. But we can't take a star and dissect it the way that we can a frog in the lab or biology class. But for stars that are pulsating, these acoustic waves travel through the star very similarly to the waves produced by earthquakes on Earth. So we use the seismic activity of the Earth to get a picture of the interior by studying the waves and how they're propagating through the interior. And likewise, we can use the acoustic waves to test our equations of stellar structure. Okay? So the point being, if nuclear fusion, because we build nuclear fusion into these stellar structure equations, if it wasn't nuclear fusion and if it was gravitational collapse, the rate and the total amount of energy are completely different. Okay? They are completely different. So if we were wrong on the energy generation that we put into these stellar structure equations, we would get bogus results for stellar structure that didn't agree with what we actually observe when we look at pulsating stars. Okay, so that's the overarching idea that I'm hopefully going to be getting across. Okay, and then these last components here are kind of building on the idea of stellar structure and observations that allow us to actually test our predictions. Okay, so what is stellar parallax? So we cannot say anything about the stars. Well, I shouldn't say that. It's not that we can't say anything, but it is incredibly difficult to get a good picture of what stars are and how they behave until you know how far away they are. And one of the easiest ways to do this is what's known as trigonometric parallax or stellar parallax. Okay, so the idea being that as the Earth is revolving around the sun, we get every 6 months we are on opposite sides of the sun, and that provides the baseline of a triangle that we can then use to do some trigonometry with observations of nearby stars. So the entire idea is if I have a nearby star and I have stars that are sufficiently far away in the background, okay, I can look at this close star with a telescope on Earth, and if I'm at this point in the Earth's orbit, I will maybe see these few stars in my picture. More than likely, what you would actually see is all of the background stars within a given field of view, but they look shifted relative to each other. Because when I'm on the other side of the Earth, or I'm not on the other side of the Earth, but when I'm on the other side of the sun and I take a picture of the same star, now my view has shifted a little bit. So originally my direct line of sight might have been pointed at this red star, and now it seems to be pointed at this blue star. And so what we actually do is we take these two pictures that are taken 6 months apart, and then we line up the background stars and see if any other foreground stars have shifted. And if they have, then we can measure this angle P, and this handy dandy formula, the distance, it can be calculated in parsecs if P is measured in arc seconds. And this just gives us directly a parallax or a distance from the parallax angle. So this is by far the most reliable way to get distances to the nearby stars. And this is very, very, very important, right? Because if you can get distances to the nearest stars, then a couple of things happen. Number one, you can then automatically say, you can't necessarily say how far these stars are, but you can say they're sufficiently far that they don't give you a parallax. So whatever your limiting parallax angle is based on your instrumentation, which is a result of the aperture of your telescope mainly, but in modern day, it's also related to your sensor, your camera sensor. Okay. So, but again, it's mostly dictated by your aperture of your telescope. Let me be clear, given the fact that we can't change our baseline. Okay. Now, that's changing with satellite technology, and we'll talk about a satellite that is changing that in great detail. We're not going to talk about it in great detail, but it's changing that fact in great detail. We will talk about it a little bit, though. But so the whole idea is, so an arc second, just for context, an arc second is, so when you look at the sky and you go straight above, you're looking straight up. If you go from that point down to the horizon, that's 90 degrees, right? So there's 90 individual little tick marks from your zenith to your horizon. Each of those degrees can be split up into 60 pieces that we call arc seconds, or I'm sorry, arc minutes. And then each of those can be divided up into arc seconds. So one arc second is 1/3600th of a degree. Okay, so 90 degrees from zenith to horizon, and each one of those little 90 pieces can be split up into 3,600 pieces. Each of those is an arc second. So these angles are extremely small, and that's why this equation works. Okay, in fact, this equation is an approximation of a trigonometric property, but it has a sufficiently small angle that we actually can get rid of the trigonometric function that goes in there, and we can use the small angle approximation, and it reduces down to this. So if the angle is measured in arc seconds, then the distance is measured in parsecs. So a parsec just happens to be 3.26 light years. Okay. Once we have the distance, we can then compute the absolute magnitude, this capital M. Okay. So this equation is known as the distance modulus. Your lowercase m here is what's known as your apparent magnitude. And your apparent magnitude is how bright you appear from Earth, okay? How bright a star appears from Earth. But your capital M is how bright you would actually be at a standard distance, okay? So the standard distance that astronomers have agreed upon is 10 parsecs. So in other words, regardless of how bright you appear to us now, how bright would you appear if you were 10 parsecs away? And so the distance modulus is calibrated such that whatever your apparent magnitude is, however bright you appear to us, if we know how far away you are, this distance d, which is what we computed from here, just plug in that distance d into this formula. And by the way, this is a base 10 logarithm. Okay, this is not a natural logarithm. This is a base 10 logarithm. But if you can do that, then it automatically computes the difference between what your magnitudes would be, and therefore you can then calculate your absolute magnitude. Now, one little note is that absolute magnitudes, both magnitude scales, as a matter of fact, kind of run a little bit counterintuitively. Number one, brighter magnitudes are smaller numbers, and it's a logarithmic scale, okay? So it's not a linear scale. So just be aware of that. We don't have to go into all of the details there, but just be aware of that, okay? So for nearby dim stars, their apparent magnitude, if they're closer than 10 parsecs, Alpha Centauri and Proxima Centauri both, they're only a little bit over 4 light years away. But they're relatively dim, okay? So being as they're closer than 10 parsecs, if we moved them out to 10 parsecs, they're automatically going to dim. And so their absolute magnitude would be much dimmer, maybe not much, but at least dimmer than their apparent magnitude. But a star like Betelgeuse, which is much further than 10 parsecs away, but is still really, really bright. If we moved it to 10 parsecs away, it would be extremely bright, okay? So it really just does depend on the individual properties of the star and where they're located relative to us now as to what their absolute magnitude would be. Okay. But so the entire idea here is that we get these distances that allow us to actually compute. So your absolute magnitude is a measure of how bright your star actually is. Okay. How bright your star actually is. And that brings us to the HR diagram. Okay. So the HR diagram stands for the Hertzsprung-Russell diagram. And the Hertzsprung-Russell diagram is a way of looking at stars by plotting their temperatures against their brightness. Okay, so here we have luminosity, but you could just as easily substitute luminosity with absolute magnitude, and you would get the same shape of graph. Okay, assuming that you put brighter magnitudes going upward and dimmer magnitudes going down, but you get the exact same shape. But so the entire idea of the HR diagram dates back into the early 1900s. Okay, and two researchers, Hertzsprung and Russell, were working independently, and one of them, Hertzsprung, actually published first, but he didn't include an actual diagram. He just had tabulated data. And then I think it was 1912, but we have the paper here, so I'll pull it up. Russell published in the journal Nature, okay, 1914. So he published in Nature, and he published this plot, okay. Now, the idea is that the horizontal axis here is your spectral type of star. Okay, so just a couple of, it was more than a couple, but it wasn't, but less than 20 years earlier had the spectral classifications really kind of been solidified. And what we mean by spectral classifications are these letters: M, K, G, F, A, and B. Okay. And these came out of the Harvard astrophysics. Okay. There was an astronomer named Edward Pickering, and he employed many women as computers to do a lot of the heavy lifting calculations, the tedious calculations. But they weren't just manual math labor. Many of them made very novel and very useful discoveries while working for Pickering, and to his credit, he gave them credit when they made them, which was rare at the time. Okay. But so this article by Russell in 1914 is basically plotting the spectral type, and the reason this is important is because the spectral type is related to the temperature of a star. Okay, that's ultimately what was discovered by Annie Jump Cannon when she was a computer for Edward Pickering. So she helped kind of solidify the nomenclature that's used with these spectral types. But you can see that there is kind of a pattern here between these two lines, the two solid lines. The vast bulk of our stars here fall in these lines, and again, this is your absolute magnitude scale, and it runs negative number or smaller numbers are brighter. So if I have an absolute magnitude of -4, this is just an exceedingly bright star. Okay, this star is an exceedingly bright star, the brightest star in this sample. This would be the second brightest star in the sample. But most of your stars lie between these two lines, right? And then you get a few stars down here. You get a few stars up here, and then you get one lonely dot way down here, okay? And Russell didn't really know what to do with this. But it was curious. And so a lot of people, as the trigonometric parallax was expanded in the 19 teens, 1920s, 1930s, more and more stars kept getting added to the diagram. And even though Russell was the only one who published a graph, because Hertzsprung published the same type of data in tabulated form, they both get credit for the diagram. It's called the HR diagram. And so more and more stars were added to it over time, and a clear pattern emerged. And that's where we get this kind of graph. Okay. So today we recognize that this strip, which is actually these two solid lines, this strip that runs right through the center from corner to corner is called the main sequence. Okay. And this is where stars spend the vast majority of their lifetime. Okay. This is their hydrogen burning phase. This is when they're burning hydrogen in their core. And then you have your red giants. So these are stars that G, F, and A type stars, when they age, when they hit the point where they start to burn helium. Now, this is a simplified picture, but when they start to hit helium, they will leave the main sequence. And because of the physics going on in the core, the burning the helium is hotter. That means that the outer layers of the star have to expand to accommodate the heat. As the star expands, it becomes a giant. Okay? And the same process happens with the supergiants. It's just that these are incredibly bright stars. Okay? These are super large stars. But you can get supergiants from your A and B stars as well. Okay? And notice that you have your temperature range here, and this is a logarithmic scale, right? So from 3,000 to 6,000 Kelvin, and by the way, our sun is right here. We're still in the main sequence. We're almost smack dab in the middle of our lifetime. So the span between 3,000 and 6,000 degrees is here, and then we span 4,000 degrees here, and then we span 15,000 degrees here. So this is not a linear scale. Okay, so do be aware of that. But it's easier to group stars by their originally proposed spectral type. And it spreads the stars out into a more discernible pattern. Okay, which is why we kind of do it that way. But again, so this was not possible to do until you knew the distance to a star so you could measure its absolute magnitude. Okay. Now we have a satellite that's doing this en masse. It's called the Gaia satellite, and it's been in operation for several years now. And the entire point of the satellite is to do trigonometric parallax in different colored filters to get an estimate of the temperature of the star based on the color differences between the two filters, if a temperature difference hadn't been known before. For the stars that have already been well measured with the temperature, the color differences have still been measured, but they're less important than for the stars that haven't been before. But what that does for us, with the Earth, we're just limited to this baseline of our orbit. But if you put a satellite in a wide orbit, you can expand your baseline considerably, which allows you to measure further and further stars. Okay, so using the trigonometric parallax of the Earth, you could get out to about 500 light years. Okay, you could get out to about 500 light years, a little bit more if you were extremely careful. Gaia is able to measure stellar parallaxes and therefore trigonometric parallax distances into the thousands of light years. Okay, so almost an order of magnitude more in precision. And given the fact that we're now looking at a volume of sky around us where we have an order of magnitude better precision, that correlates to far more than an order of magnitude of the total number of stars that we can look at and measure with any sort of precision. And so the Gaia satellite currently, the Gaia satellite's HR diagram, okay, so this paper is the Gaia Data 2 release. And I mean, it's not uncommon in physics, especially if you're on a large collaboration with a particle accelerator, for example, to have just hundreds, if not thousands, of authors on a paper. It's a little less common in astronomy unless you're on a major satellite. Okay, so if you're part of a collaboration with a major satellite, then you're going to have hundreds of co-authors, if not more. But so this paper is basically detailing the information contained in the second release of data from the Gaia satellite. And one of the things they focus on in this paper are HR diagrams for various types of data that they collected. Okay. And so the complete HR diagram looks like this. Okay. And so this GBP and GRP, those are the blue and red, Gaia blue and Gaia red filtering that I was mentioning earlier. It takes pictures in different filters, and then it'll take differences in those filters. And as you can see, there is at least a relationship between what the magnitude difference is in those filters, and there's a direct correlation. It's not linear, it's still logarithmic again, but there is a relationship with the temperature. Okay, and then using the trigonometric parallaxes that it's able to measure, we can get absolute magnitudes. Okay, so now when we say capital M sub G, what we mean here is the absolute magnitude in the Gaia bandwidth. Okay, so in other words, Gaia does not have access to all available electromagnetic wavelengths. But within the wavelengths that it does have access to, it integrates the entire total brightness of a target across all of those available wavelengths and adds all of those brightnesses up into a total brightness, and therefore a total absolute magnitude, and that is what we have. And now you can see just how precise this is. So your main sequence is right here. The scaling is a little bit different. So your giant stars are before they kind of looked like they were off the middle of the HR diagram. Here they're kind of off the top. But that's a scaling of the axes issue, not a physics, not a difference in physics issue. But now you can see that there's not a terribly clear distinction between the giants and supergiants that this graph may have seemed to indicate, right? So as you add more and more add more and more data to your plots, things get a little bit more ambiguous, right? And we also see that here, right? You have your very, very, very well-defined white dwarfs here. And then you have stars that are almost on the main sequence, and then yet again still almost on the main sequence, but where exactly does the main sequence end and the white dwarfs begin? Perhaps somebody who's read the papers more in depth than I have can answer that, but there's not as clear cut a boundary, right? Which is super fascinating and super interesting. And then on this scale, we have the luminosity of the stars scaled by the luminosity of the sun. So the sun would be right here on this diagram, maybe right about here. The sun would be right about, it needs to come down a little bit, yeah. Right about there, okay. So the sun is right about here on the diagram. And so then stars that are 10 times as bright are here, 100 times as bright are here, 1,000 times as bright, and 10,000 times as bright. But one thing that this chart does give is you don't really see too many stars above 10,000 times as bright as the sun, which suggests an upper limit of the total brightness a star can have, which is something we have. The physics seems to have indicated that there should be an upper limit, and that's what we see. So that's pretty comforting. If we saw, something that was 1,000,000 times the luminosity of the sun, like if we saw several stars, then that would kind of challenge things, challenge some of our theories. But it's comforting to see that what we expect is what we see. Okay, now to the meat. To the claim that Kent Hovind was making, okay? Gravitational collapse versus nuclear fusion. So to make the arguments here, we have to define some constants. Number one, Newton's universal gravitational constant in SI units, and I prefer to work in SI units because it's what I grew up on. The textbooks that I used were SI units, so it's what I'm most comfortable with. So anyone who doesn't like the metric system, well, sorry. But in SI units, the Newton's gravitational constant is 6.67 times 10 to the negative 11 meters cubed per kilograms times second squared. The mass of the sun, although not constant, it's pretty darn constant, especially over the course of a human lifetime. And it's really close to 2 times 10 to the 30th kilograms. The radius of the sun is really close to 7 times 10 to the 8th meters. The luminosity of the sun has been measured to be 3.86 times 10 to the 26 watts. And the speed of light is 3 times 10 to the 8 meters per second. Okay. Now, gravitational collapse. It can be shown. I don't go through the derivation here, but I might do a supplemental video for this lecture, or this critique response, however you want to phrase it, and go over the calculation to get that number. But in any case, the total energy available from gravitational collapse is really close to 3/10 times the gravitational constant times the mass of the sun squared divided by the radius. And if you punch in G, M, and R into this equation, you get 1.1 times 10 to the 41st joules. Okay? But power, and by the way, luminosity is power. Okay, so luminosity is the total energy that a star is giving off per unit time, and that's the definition of power. So power is energy per unit time. Therefore, time is energy divided by power. So a rough approximation for the total amount of time the sun could shine if it were powered by gravitational collapse, I just take the energy from the gravity that's available, divide it by the rate at which it's shining, and this gives me 2.85 times 10 to the 14 seconds. And if I convert that into years, it's about 9 million years, or just shy of 10 million. Given the fact that we're really confident the sun is 4.5 to 5 billion years old, that's a problem. Okay. So, right off the bat, now, I'm not going to go into the arguments for why we think that the sun is 5 billion years old in this video. Okay. That's kind of peripheral to my purposes here. And doing so would require a bit of time on its own. So I'm going to leave that alone, but just understand that we have reasons we think that the sun is 5 billion years old or thereabouts, right? But what kind of time scale do we get from nuclear fusion? Okay. So E equals mc squared, right? This is, of course, Einstein's most famous equation. And so from nuclear physics, we know that 4 protons go into creating a helium nucleus. Glad I actually still have this editable. And so these 4 protons go into creating the helium nucleus. And then a little bit of the initial energy wrapped up in the initial 4 protons gets converted into energy. Okay. And then we also get a smattering of neutrinos and stuff, right? And no, that was not a typo for the stuff. I like to call it stuff. But so the vast majority of the total amount of energy available in the initial 4 protons goes into the helium nucleus itself, 2 protons and 2 neutrons. But you do get a little bit of energy generation from that process. And then you get, the neutrinos. But the neutrinos and the stuff is such a small fraction that it's really negligible for our purposes here, at least to get a rough estimate of what's going on. So particle physics has given us the answer, or at least the number, that the amount of energy that is generated from the initial 4 protons is 0.7% of that total initial energy from the 4 protons. Okay, so effectively 99.25% goes into the helium nucleus, 0.7% goes into the created energy, and then what's left over goes into the neutrinos. Okay. So to get a rough estimate of the time scale for nuclear fusion, just go ahead and throw out a reasonable ballpark number for the fraction of hydrogen in the sun that's available for fusion, and call it 1/10. Okay. So let's say 1/10 of the total amount of hydrogen in the sun. And by the way, the sun is nearly all hydrogen. So for a rough calculation, you can say, we'll just assume that the sun is entirely hydrogen. It's not at the current time, but it almost assuredly would have been mostly hydrogen. It still is mostly hydrogen, but would have been even more so when it was a protostar and a very young star. So for a rough number, this is perfectly fine. So what we're going to do is we're going to take this m, but we're going to use the mass of the sun mitigated by the fact that only 0.7 of it is actually going to go into energy, and only 1/10 of it is available for that process. The E equals mc squared process. So 1/10 times 0.007, or 0.7%, times the mass of the sun times the speed of light squared, and we get 1.3 times 10 to the 44th joules. That's 3 orders of magnitude more than what we got with the gravitational collapse. That's 1,000 times more. Which, if you do the exact same kind of calculation for the time, that means you get 3 orders of magnitude more. And given that our coefficient is 1.3 instead of 1.1, and our result here was 9, it's perfectly reasonable just to round that up to 10 to the 10 years, or 10 billion years. So just this very rough approximation gives us already a very clear, distinct front runner. Okay, so even if we say, let's assume the question is not yet settled, whether it's nuclear fusion or gravitational collapse. This right here by itself, if we accept the idea that the sun is roughly 5 billion years old, then it clearly puts nuclear fusion at the front of the race. Okay, clearly puts nuclear fusion at the front of the race. We're going to put this energy generation idea on hold for a moment, and we're going to talk about next variable stars and stellar pulsation. Okay, so stars can pulsate, all right? And this is a light curve of the star Delta Cephei, which is the prototype of what's known as the Cepheid variable class of pulsating stars. And so a light curve is simply you're measuring the luminosity, or we measure the apparent magnitude. If we know the distance modulus, we can get the absolute magnitude. But even if you don't know the distance or the absolute magnitude, you can at least see how the star varies over time. Okay, so you're basically taking a measurement of its brightness as seen by your camera and telescope setup, and then taking measurements of that star at different times. And if it varies, especially in a very cyclic and regular way, then that's evidence of a very periodic process. Some sort of physics is happening inside the star. Okay, so Cepheid variables are an extremely important class of stars for multiple reasons, but one of the main reasons is their brightness variations can get quite high. So remember that I said this is a logarithmic scale. Magnitudes is a logarithmic scale, and we see that this dips from almost a magnitude of 2.15, which is okay. So we're talking about differences in magnitude. This is not absolute magnitude, but you're going from 2.9 to below 2.2. So it's not quite stretching an entire magnitude in difference, but it's close. Okay. And one magnitude corresponds to 2.5 times difference in brightness. Very noticeable, okay? If you had a magnitude 2 star that was typically a magnitude 2, and you saw it brighten on a given night up to magnitude 1, you would notice that, okay? That's easily noticeable with the naked eye if it's a naked eye object. And so these stars started to be discovered in the, early 1900s, okay? And Henrietta Swan Leavitt, who's pictured here, was another computer for Pickering, and she did a lot of work with these types of Cepheid variables. And she had access to data from the Small Magellanic Cloud, and that was very fortuitous because these variables are bright enough and big enough. These are subgiant to giant type stars, so their luminosity is huge. We're talking about stars that are kind of like here. Okay, so their luminosities can be 100 or more times brighter than the sun, and so that means that we can see them in other galaxies. right? So these particular measurements that she was making were all done by this in the Small Magellanic Cloud. And so what that did was, even if you don't know the distance to the Small Magellanic Cloud, if they're all in there, then you can say that they're all at least very close to the same distance away. And then you can compare how bright they look and get a sense of which ones are brighter and which ones are dimmer intrinsically, right? Because if they're all the same distance away, even if you don't know what that distance is, whichever ones are brighter, those have to be brighter. Whichever ones are dimmer, they have to be dimmer. And what she noticed was, so these Delta Cephei, the Cepheid variable stars, again, Delta Cephei is the archetype, they have this kind of weird light variation where they rise rapidly in brightness and then they decline a lot more slowly. But then the cycle just repeats. Okay? And you'll notice this is on the scale of days. Okay? So from here to here is effectively the same point in the cycle, and we can see that because we have this little hump right here, and we have that little hump right here. So if we go from here, which is just shy of 0.5 days, up to effectively 5.7 days, so like 0.4 days up to 5.7 days, that's 5.3 day period. Okay, so this star changes brightness about every 5.3 days. Okay, so Cepheid variables have variations on the order of days to weeks to months, and they have extremely bright magnitude changes, and this allows them to be seen at great distances, which is really advantageous. So what she noticed, what Henrietta Swan Leavitt noticed, was that if she measured the magnitudes or the luminosities when the stars were at their brightness peak or their brightness minimum, they fell onto these two trends. Okay? So once again, the vertical axis is brightness and the horizontal axis is the period, or this, in the case of Delta Cephei, the 5.3 period day. Or the 5.3 day period, I should say. So this graph is the data as they are, and then this data is set on a logarithmic scale. And again, the original paper was published. Okay, so again, this is kind of how things were done. You see that this particular paper, Periods of 25 Variable Stars in the Small Magellanic Cloud, was signed off on by Pickering himself, but he makes the note right up front that the following statement was prepared by Miss Leavitt. Okay, and again, this was not common at the time. Okay, women were not really astronomers outside of a few certain circles, Pickering's computer group being one of them, right? And again, he was also very generous with giving the credit where credit was due. And so she was the one who did the work on these variable stars, and she noticed that there's a very clear trend between when the stars are at their brightness maximas or their brightness minimas and the period of oscillation. Okay? And so this is what's known as the period luminosity diagram. So what this tells you is if you have a Cepheid variable star, you can plot the period if you can measure the period over the course of, days, weeks, months, if you can get a reliable period, you can immediately put it on this graph and say, you can read right off about, at least to within some margin of uncertainty, how bright it should be. This is groundbreaking. Okay? This is absolutely groundbreaking. So in just a few years, okay, this was done in 1914, or was this the 1912 paper? It's been a long day, so bear with me. Yeah, so this was 1912. So between 1900 and 1920, we have stellar parallaxes being measured. We have the invention of the HR diagram. We have this period luminosity relationship diagram, which allows you to say how bright something is if you can measure its oscillation period if it's a Cepheid variable type star. If you can do that, then you can reverse engineer the distance. So now all of a sudden, if you can measure the period of a Cepheid variable, you can plot it on this diagram, and you can get the total luminosity, and then you can go back and compare how bright does it actually look, how bright is it, and now you have the lowercase m and capital M in the distance modulus, and you can solve that equation that we looked at earlier for D. So now, all of a sudden, you have a probe to distances that you didn't have before, because these things can be seen much further away than the trigonometric parallax would allow. Okay? Much further away than the trigonometric parallax would allow. So, this was absolutely groundbreaking. Okay? Now, going back to the HR diagram, as these types of variable stars and a few other types of variable stars were discovered, people started to realize how the HR diagram was working. Originally, okay, if we come back up here, originally, when Russell and Hertzsprung were submitting their work and people were kind of making the connections, oh goodness, there's a direct correlation between the temperature of a star and its luminosity. What the immediate thought was, once it was kind of realized that this was your hydrogen burning phase, okay, and we really kind of realized that this was hydrogen burning in the 1920s and 30s, okay. It was really firmly experimentally established in the 40s and 50s, if memory serves, but the theoretical groundwork was really laid in the 1920s. One of the major players, Cecilia Payne, okay? She was also at Harvard, but she wasn't a computer. She was actually the first female student to get her PhD from Harvard as a female in astrophysics. Okay, so Harvard was breaking all of the glass ceilings. But anyway, her work was extremely instrumental in establishing the fact that stars were made up of hydrogen, mainly hydrogen. And so it was initially thought that a star was born really big and really hot, and as it went through its life cycle, it cooled down and got smaller, which on the face of it is a reasonable assumption. But it pretty quickly became clear that that's not what's happening. Okay, so the accepted idea of stellar evolution now, and again, this kind of touches on the overarching theme of what this video is going to show you here in a little bit. But again, it's kind of a peripheral thing. But the idea is that a star comes onto the main sequence based on its mass that it has when it's a protostar. Okay. Early on in the star's life cycle, when it's just starting to shine, the nuclear fusion is just starting, that fixes where you're going to be on the main sequence. And then as you burn through your fuel, what happens to you when you're done burning your hydrogen is what dictates what will happen. If you're down here with the red dwarfs, not much really happens. You burn up your hydrogen and that's it. They're not, most of these are not, especially the ones down here at the tip, they're not big enough to ignite helium fusion, and as a result they just collect helium and you just have giant balls of helium floating throughout the universe. However, that hasn't happened yet because the lifetime of these stars is 100 billion years. Once you get up into stars like the sun, now these stars can go up into the giant branch, which the sun will eventually do. And once they exhaust all of their fuel that they possibly can fuse, then stars like the sun come down here to the white dwarfs, and they will basically live out the rest of the universe as collections of nuclear material with degenerate electrons, effectively. Your really hot stars, when they burn up their fuel, their hydrogen fuel, they become giants and supergiants. And then when they are done burning their elements up through iron, these are the objects that can become neutron stars and black holes. Okay. But, so coming back to the pulsating variable idea, the Cepheid variable idea, so this light variation, by the way, is stellar pulsation. Okay. So this light variation is literally the layers of the star that actually emit the light that we see expanding and contracting. Okay, so these are the outer layers of the star literally doing this. All right, and so as more Cepheids and other types of variable stars were discovered, we realized that there's a region on the HR diagram called the instability strip. That if a star is in this region, it has a really good chance, if not a better than good chance, of being a pulsating star. And the reason is there's a property of gases inside stars called the opacity. And this is a resistance to the energy generated in the core. The energy generated in the core has to work its way out to the surface of the star. Okay. But there's a lot of stuff in the way. And so the opacity is a measure of how much an individual amount of energy is scattered before it reaches the surface. That's a very simplistic way of thinking about it. But so it's kind of like a resistance to the flow of light, if you will. So the opacity is this parameter kappa. And if you have a region where the opacity can be written as a power law of the stellar density in that region and the temperature in that region, then energy can get dammed up in those layers. So the typical, the usual suspects, if you will, are hydrogen and helium layers in the outer layers of the star, not quite in the atmosphere yet, but they're toward the outer edges of, toward the photosphere. And energy coming out from the core will go into ionizing the atoms in this region. Okay, if the opacity is of a power law form of a positive exponent with the density and a negative exponent with respect to the temperature, if you can write your opacity in that way, or if your opacity obeys a law like that, then it's much easier for the hydrogen and helium atoms in those regions to be ionized. So the energy is effectively absorbed by the atoms, ionizing or knocking the electrons out and thus ionizing them. But that creates, or I shouldn't say it creates, but it deposits heat into that layer because the photons have energy. And if the energy is not being let through, then that layer has to heat up. As the layer heats up, ideal gas law. If your pressure doesn't really change all that much, but T goes up, then your V has to go up, so the layer expands. But as it expands, it cools down. And when it cools down, the electrons can recombine and you collapse back down. And so you just get this pulsation and what we call, this process is known as Eddington's thermodynamic heat engine or the Kappa mechanism. Okay. So if you are in this region of the instability strip, then you have a really good chance of pulsating due to this Kappa mechanism. Now, my particular stars, well, first things first, you can see that the classical Cepheids are well above the main sequence. These are in the giant branch. Our Lyra stars are a really, really important class of variable stars. They are a little bit closer to the main sequence. They're slightly evolved. The stars that I study are not on this chart, but they're called Delta Scuti stars, and they are actually where the instability strip and the main sequence meet. Okay. A quick side trip to eclipsing binary stars. And eclipsing binary stars, these are going to be super important here in just a little bit. Okay. But, so an eclipsing binary system is simply what it sounds like. Binary meaning two, so I have two stars. And they're orbiting each other just like planets orbit suns. There's nothing preventing stars from orbiting each other, and they follow the same laws insofar as things like Newton's universal law of gravitation, Kepler's laws, conservation of momentum, conservation of angular momentum, conservation of energy. They follow all of your mechanical conservation laws. Unless you have some sort of energy degradation and spiraling in due to any external influences, or due to the aging of the stars. If one of them enters the red giant phase and the other component starts eating matter from the outer layer of the giant star, then that can cause issues as well. But outside of those, if your two stars are what we call detached stars, meaning that both of your stars are essentially still spherical, then what happens is this. When the two stars are oriented such that neither one is blocking the other one, if you take measurements of the total light output of the system, you get a rather constant line. But when one of the stars blocks the other one, you'll get a dip in brightness. And then when that eclipse is done and they go back to, you see both of them together, you get a constant line. And then when the eclipse happens in reverse, the star that was eclipsed is now doing the eclipsing, then you see a second eclipse. And then when the two stars are not eclipsing each other, you see this, and this just repeats. Okay? Now, there's no shortage of to ways that eclipsing binary light curves can look. This is a very simplified picture, but this is a very common picture too. So it's usually typical that you'll have a small dim star orbiting well, I shouldn't say orbiting. They're orbiting each other, but you have a small dim star and a larger, brighter star in your system. Okay, and they're orbiting a common center of mass. The brighter star, when it's eclipsed, because you're blocking light from the brighter object, you're typically blocking more total light. And therefore, you get a deeper drop in brightness, and therefore, we call this the primary eclipse. When the dimmer star is blocked, you're not blocking as much total light from the system, and therefore you get a much shallower eclipse. So for systems where you actually have very discernible differences in your eclipse depths, you can immediately say, oh, this is the primary eclipse, this is the secondary eclipse. Not all eclipsing binaries allow that, but some do. If you can also perform spectroscopy, then you can get radial velocity curves from the Doppler effect. So the Doppler effect is going to look like a sinusoidal curve, but the speeds of the stars are really not being sinusoidal, but your ability to detect their speed is. So the Doppler effect is most effective when things are oriented such that they're moving away from you directly or directly toward you. And that's what's happening, for example, in this part of the orbit. The yellow star would be moving nearly directly away from you, and the red star would be moving nearly directly toward you. And so your radial velocity measurements are going to be at a maximum displacement for those two points, for those two objects, but one of them is going to be positive and one of them is going to be negative. In this case, the orange star, or the yellow star, is moving away from you. That is defined as a positive radial velocity. When things are moving toward you, that's a negative radial velocity. Then, when the red star is moving away from you and the yellow star is moving toward you, then you get the opposite, or the graph flips, and that's exactly what sine graphs do, right? You get a wave where at one point you have a maximum, half a wave later you get a minimum. So here would be the start of your sine wave, if you will, and half of a wave later, you're at a minimum if this was a maximum. Okay. So you go from a maximum to a minimum when you're going from moving toward to moving away, and then you would go from a minimum to a maximum if, I'm sorry, you go from a maximum to a minimum if you're initially moving away and then toward, and then you would go from a minimum to a maximum if you are moving toward and then away. Okay. So how does this help us? So eclipsing binary stars is one of the best ways to independently measure the mass of stars. Okay? It's absolutely one of the best ways to measure the mass of stars. If you can combine both of these types of measurements, photometric measurements or light measurements, and radial velocity measurements, then these relationships have to hold. So what this is telling you is that the velocity of your primary to the velocity of your secondary, so the primary would be the yellow star, the secondary would be the red star, the ratio of those velocities has to equal the reciprocal ratio of the masses. So in other words, typically your the velocity of your primary is going to be smaller than the velocity of your secondary because your primary is typically bigger. Therefore, it's not going to move as much, whereas your secondary is going to move quite a bit. And the extreme case of this you can think of as planets. If the primary were the sun and the secondary were a large planet, then the planet is going to do most of the orbiting, and the star is going to wobble just a little bit, okay, as the planet orbits. And so the velocity of the primary object is typically going to be smaller than the velocity of the secondary object. But that means that the mass of your secondary object, because it's moving a lot more, it's basically tied to the heavier object, its mass has to be smaller. So if the velocity of the primary is smaller than the velocity of the secondary, then the mass of the secondary is going to be smaller than the mass of the primary. And Newton's universal law of gravitation also is going to hold, as well as Kepler's third law. So Kepler's third law relates the period and the size of the orbit, or the semi-major axis, to the total mass in the system. Okay, so using the light curve, if I can measure the time from here to here, I can get the orbital period. Okay, and using this, I can get the ratio of the masses. And I can estimate the size of the orbit based on the light curve as well. And that allows me to compute the total mass in the system. Okay. This really does deserve a little bit more explanation. Okay. The size of your orbit. Okay. Think of a circular orbit. All right. So these maximas and minimas represent the actual velocity the stars are moving with. The sinusoidal nature is the effect of our line of sight with respect to their motion. Okay, so their actual speed isn't changing. Our ability to measure their speed is. But if you know the speed and you know the period, then you can get the size of the orbit. And that's what allows you to compute the total amount of mass. Then using the ratio of those velocities, you can get the ratio of the masses. And if you know the total mass and you know the ratio of the masses, you can work out what the individual masses are. Okay, so this is terribly, terribly convenient, right? Our next slide is modeling stellar pulsation. And so I'm going to pause it here, top off my coffee, run to the restroom, and then we'll be right back. So hold your horses. And we're back. Okay. So, modeling stellar pulsation. How do we actually predict this kind of behavior, right? Where the layers of the star expand and contract. Well, to start, we have to actually model the star. Okay, and when we say model the star or compute its stellar structure, what we mean is, okay, we know it's mainly hydrogen, possibly some helium, more than likely some helium, but at least a minimum of 70% hydrogen, maybe 27% helium, and maybe a smattering of other things, depending on what initial conditions we want to use. But assume that I know what the stuff is and how much of it I have. Assuming that nuclear fusion is taking place, how then do the things like the density, the pressure, the temperature, and the luminosity distribute themselves throughout the star? In other words, if I look at the pressure profile, how does it change from the core, where the pressure has to be immense, out to the edge? How does the density, the core is not quite simply nuclear material the way that a neutron star is, but it's almost all completely ionized. So you have these nuclear materials just flying around everywhere, bumping into each other. The density has to be really high compared to the outer layers, where the atoms are much, much, much more calm comparatively. Okay? So how does your density change from the center of the star out to the edge? Again, your temperatures have to be immense in the center. And so how does your temperature profile change from the core of the star out to the edge? Okay, so the entire idea of your stellar structure equations is to get a model of the star and see how these quantities are changing from the center out toward the surface. Okay. And so your stellar structure equations are given by this group of equations right here. Okay. So this first equation relate the derivative of your pressure with respect to radial coordinate is related to your local gravitational acceleration times your density. Okay. So in all of these equations, capital P is going to be your pressure. Lowercase r is going to be your radial coordinate as you're measuring from the center of the star out to the edge. G is again Newton's universal constant. M sub r is not the total mass of the star, but it's the total amount of mass enclosed by whatever lowercase r you're moving or you're at as you move from the center outward. Okay. And then rho is your density. All right. So this equation is actually called the equation of hydrostatic equilibrium. And it's one of the most important equations in all of astronomy. Okay. You cannot have a star without it being at some point in hydrostatic equilibrium. Even if it's not in technically, if it's not in hydrostatic equilibrium when it's pulsating, it was before it was on the inside the instability strip. You at least don't get the idea of stars without hydrostatic equilibrium. This equation, the derivative of your mass enclosed within some radial coordinate, not divided by, but take the derivative of your mass with respect to your radial coordinate, is equal to 4 pi r squared rho. And this is just your definition of density. Okay, this is your density is equal to mass divided by volume, but written in that's not a real word, written in the form of a derivative rather than a definition. Okay. Now, this is the equation that's extremely important for our purposes for this. Everything that I have said is leading up to this point right here. This is the crux of what Kent Hovind was talking about. This equation right here, the derivative of how your luminosity is changing with respect to its position inside the star, is equal to 4 pi r squared. Again, 4 pi r squared. And there's no secret that 4 pi r squared should be here. Okay. If you're not geometrically adept, 4 pi r squared is the surface area of a sphere. So as you are looking at the center of the star and moving outward, you're enclosing larger and larger spheres until you get to the total radius. Okay. And so how your luminosity changes with radial coordinate is equal to 4 pi r squared times your density times epsilon. But epsilon is your energy generation. Okay. And then how your temperature is distributed throughout actually depends on your opacity. It depends on your density. It depends on the temperature, and it depends on the luminosity. Okay. And by the way, it can equal either of these two expressions, and it equals this expression when you're in the radiative zone, and it can equal this expression when you're in the convective zone. Let me make sure that I have those right and that they're not backwards. Give me just a second here. Yes, that is correct. Okay, so this is radiation and this is convection. And by the way, so mu is the mean molecular weight of hydrogen. Gamma is the adiabatic constant from thermodynamics. And give me 1 second. Yeah. K is related to the total number of particles in a given amount of volume through the ideal gas law. And GM over R squared, again, is your local gravitational acceleration. Okay. So these are differential equations, but they're all coupled. Okay. So you'll notice, first things first, that your density appears in all of them but the bottom one. Okay, so when you're in the convective zone, your temperature distribution does not depend on your local density, but everywhere else it does. Okay, and so what the steps are, in general, there's no numeric or I shouldn't say numeric, there's no analytic solution to this entire set of equations, except for just a couple of handful of very idealized conditions or approximations. And so you have to use computers, but the basic idea is that your density appears in all of these equations, except unless you're looking at your temperature gradient in the convective zone. So your density is changing throughout the star, so its value is changing, which means the rates throughout the star are changing. And here you have the rate at which your luminosity is changing with respect to your position in the star, but your luminosity appears here, right? And so the entire idea is that you have to specify what you think the central conditions are in terms of the pressure, the temperature, the density, and the luminosity, and then you kind of split your star up into several layers until you get to the surface, and you compute what's going on in each layer successively. So you solve all of these equations simultaneously for a given layer, and then use that layer as the input for the next layer's values. So whatever value, let's say you have layer 1, layer 2, layer 3, layer 4, layer 5, you would specify the central values, what you think they ought to be for layer 1, and then you would use these equations to compute layer 2 based on all the values from layer 1. So you would use the density from layer 1 in these equations. You would use the total mass enclosed by the shell in layer 2 to then compute these two equations. And then you would also use the density in layer 1 to compute the luminosity in layer 2, and you would use the temperature in layer 1 to calculate the temperature in layer 2, and so on. And then you would just continually do that outward. Okay. Now, when you're done with that, you have a grid of density versus radius, pressure versus radius, luminosity versus radius, temperature versus radius. Okay. And the entire idea is that if you pick the right central values and you can integrate outward, then you should see that all of your stuff goes to zero at the surface. Your pressure, other than your luminosity. But your pressure, your total mass doesn't go to zero either. Your mass is growing as your pressure is decreasing, your luminosity is decreasing, and your temperature is decreasing. But your density should go to zero at the surface because beyond the surface there is nothing else. That's not really true in real stars when you have tenuous atmospheres, but for our purposes, if you just consider a sphere or a star as a simplified sphere, then that's true. So your density is really high in the center and it effectively goes to zero at the surface of the star. Your total mass starts out at zero and grows to the total mass of the star at the stellar radius. Your luminosity effectively is very small at the very central part of the core, and then as you move through the core where your nuclear fusion is burning, as you get those larger concentric circles, you're capturing more and more light, and so your luminosity is going to grow until you basically plateau to the total amount of light the star is making, and then that light escapes throughout the star. And your temperature is going to see a very severe drop-off, okay? In the core where your nuclear fusion is happening, it has to be extremely hot, and then you'll see as you move outward through the star, you get a sharp decrease in temperature, okay? So my contention is that it's this epsilon right here that is a huge problem for Kent. Almost got Ken Ham and Kent Hovind confused in my brain. This is a huge problem for Kent Hovind, okay? Because we can now build what we think is a reputable star, and the total luminosity of the star is dependent, and it has to be dependent on the energy generation. So this epsilon factor here, it's really innocuous. You just look at these equations and you think, well, how big of an effect can the epsilon have, right? Like you can play with it as a parameter and see how it changes things. How important is it really? But it's actually the energy generation factor. So how your luminosity changes has to be dependent on the energy generation and its source. What type of energy generation are you talking about? And that then affects your temperature distribution. And your temperature distribution is going to affect your pressure and your mass distributions because it also affects your density. Okay? So all of these are intertwined and you have to solve them all simultaneously or simultaneously numerically. And so this is an extremely sensitive set of equations to what you put into them as initial conditions. Okay? And what energy generation rate you pick greatly affects things. Now remember, we haven't talked about the rate of energy generation, but we did talk about the total amount of energy available. If you're talking about nuclear fusion, even if you say, okay, let's only assume that only about 1/10 of the mass of the sun is burning nuclear fusion or burning hydrogen via nuclear fusion, and everything else is, in the other layers doing whatever they do, whether they're in a radiative zone, a convective zone, or in the photosphere, who cares? that still is 10 billion years worth of energy. And the gravitational collapse only had about 10 million, 9 million, really. 10 million to around 10, power of 10. So basically 10 to the 7 versus 10 to the 10th. Okay. 10 to the 7 versus 10 to the 10th. So if you're going to put or try to put some sort of gravitational collapse in there only as your only source of energy generation, then the structure of your star is going to be affected immensely. Okay? It's going to be affected immensely. Now, here's where the rubber meets the road. Okay? So, the goal of modeling with stellar pulsation is you want to calculate the pulsation periods of a given star, and you have to use the results of your stellar structure models. Okay? So this equation is what's known as the linear adiabatic wave equation. And this equation is a first kind of approximation attempt at figuring out, once I have a stellar structure model complete, what ways can that star pulsate, right? In what frequencies can that star pulsate? And this equation will pull those out, at least some of them, okay? This is a simplified picture. This is in no way, shape, or form as complicated as the most sophisticated current algorithms for computing stellar pulsation models can get. But just to give you an idea of why the stellar structure equations are important, if you look at this equation, okay, the entire idea is to solve this equation for these sigmas, okay? So your sigmas are the frequencies, right, that the star can pulsate in. This zeta factor is actually the displacement function. So zeta is what we're actually looking at as doing the waving. Okay, so if you were to, like draw a sinusoidal wave, if you're talking about a sound wave, then it's actually air molecules that are doing the oscillating, as well as the pressure disturbances moving through the air is also doing oscillations. But so the material in the star is literally moving back and forth with these oscillations. And so this factor zeta measures the amplitude of your oscillations relative to the radius of the star. It's kind of like a scaling, it's a dimensionless distance, if you will. The displacement of your oscillations divided by the total radius of your star. But it's a function, okay? So zeta is a function, and it will be a trigonometric function. As a matter of fact, it'll be sines and cosines. It'll be waves. If you solve this equation, what you're really doing, I said initially you're solving this for sigma. What you're wanting to do is solve this for zeta and then extract the sigmas that go with each zeta and see what those frequencies are, and those are your predicted frequencies. Okay. But notice, okay, this depends on your pressure. It depends on your density. And so you have to have a valid stellar structure model to even put into your equations that predict your stellar oscillation modes. Okay? You have to have a valid stellar model that then you can put into the results of into this equation. So this P here is not the pressure at a given point. It's the entire array of pressure that you had corresponding to each radial value. Okay, so this P is actually a function, because I'm also going to be taking the derivative of this entire parenthesis, my pressure being one of them, and it's a function as how my pressure changes from the central cell that I picked outward, or my grid, if you will. Okay. And then I have to do the same thing. I'm not taking derivatives of the pressure or the density here or the pressure here, but they are going to appear in the total equations once I've taken the derivatives here in this set of factors and here. And gamma 1, the gamma 1 here is the specific heat of the gas in the layers in question. Okay, and that can change based on where you are in the star. So you have a lot of different varying quantities in here. And so you have to know what the stellar structure is. So what I'm really driving at here is we would not be able to predict the specific frequencies that we do, or we would not be able to predict valid frequencies if the energy generation were not correct. I need to drive that point home because we're already almost 2 hours into this thing. We would not be able to predict the correct pulsation frequencies if we didn't have the correct energy generation. And so the claim that, well, it could be gravitational collapse, it could be nuclear fusion, frankly is as close to balderdash as a scientist would ever say. We cannot, or I shouldn't say cannot, but we generally don't like to use the word proven. I can't prove to you that this process is correct. I can show you it builds an extremely consistent picture with nature. Okay? It builds an extremely consistent picture front to back of what we know about stars. Their distances, how we measured their luminosities, then being able to use those luminosities to say something about the pulsation periods of stars that are pulsating, and then being able to use the theory of stellar structure to predict what those pulsation periods ought to be. And we would not be able to do that accurately if the nuclear generation rates were wrong, or if we were using the wrong type of energy generation rate in the first place. Okay? So that is why this is such a crucial step. All right? We're not going to go through the math of solving this equation. Okay? I'm leaving a lot of physics on the table, and this presentation's already going to be math heavy enough. And I'm still leaving a ton of math on the table. I may do a follow-up video that actually goes through some of the derivations if people in the comments want some. But for now, for our purposes, all I need to drive home is that this equation is one of the first approximations to getting actual physical results under an idealized set of circumstances. And even under those idealized circumstances, you still have to have that stellar structure model done to plug the functions of your pressure, density, and so forth into this equation so you can take the derivatives properly and compute what these displacement functions ought to be and their corresponding frequencies. Okay, so that's the idea. So the energy generation, okay? So this little innocuous epsilon right here in this, third stellar structure equation. The energy generated in main sequence stars is by far and away done by two processes. Either what's known as the proton-proton chain, where protons are literally colliding into each other and creating intermediate nuclear structures until they reach a helium nucleus, or the CNO cycle, where carbon, nitrogen, and oxygen, if they're available, are also acting as catalysts to allow protons to collide into helium nuclei. Okay, so the energy generation from the proton-proton chain, this is coming straight from atomic physics. So again, as I said, I'm leaving a lot of physics on the table. I'm not actually showing you an explicit example of how to solve this equation, and I'm not going to go into the physics of where these equations come from. I can give you the references and you can look at them yourself, but again, to get into the derivation of where these expressions are coming from would be the length of this video itself plus. Okay, so for the moment, we're just going to take the word of atomic physicists and say that they know what they're talking about. All right. But so the energy generation rate in a proton-proton chain, so the idea of the proton-proton chain, again, is you have 4 individual protons. They come in and they collide with each other, but they don't just necessarily all 4 come in and collide all at once. You have a proton and a proton come in and collide, and they might collide and create a proton and a neutron and some neutrinos and whatnot. And you might have 2 of those, a proton and a neutron and a proton and a neutron, that come in and collide and eventually create a helium nucleus. And then the total amount of energy that was lost is that 0.7% of the total rest energy of the initial 4 protons. Okay. But there are various ways in which the proton-proton chain can happen. That way is not the only way. But at the end of the day, whichever, what they call the branches of the proton-proton chain, as long as you start out with 4 protons and you end with a helium nucleus, then you have gone through the proton-proton chain. Okay. So the proton-proton chain energy generation rate is given by 0.241, which is an empirical coefficient determined experimentally by atomic physicists, times rho, which is the density of the medium in which the collisions are happening. In this case, it's the density of the core, which is sensitive to the stellar structure equations, because you have to know what the density is to actually get the generation rate. So again, these equations are coupled, and you have to solve them all simultaneously. That's all that that's saying. So the x is the fractional mass. What fraction of your mass is the given object in question? In our case, the 2 things that are colliding, I really should say. So in our case, they are both protons that are colliding, so they're going to have the same fractional mass, and that's why this quantity is squared. FPP is a factor, and I want to get this. I want to make sure I get this one right. So let's look this one up and make sure that we have these next few coefficients correct. Yes, FPP is what they call the screening factor, and because this is hydrogen we're talking about, you'll also have free electrons running around your plasma, and so the free electrons can kind of create like a screening. So, if you have a proton here and a proton here, if they're by themselves, they're going to feel their total coulombic repulsion, because they're going to repel, right? Their positive and positive charge naturally wants to repel, and so they're going to see each other's fields completely if they were in a vacuum. But because you're in a highly charged plasma, they see each other both as positive charges, but if there are free electrons, moving through here, it kind of effectively creates a shield, a little bit of a screen, so you don't see the total effective charge of the other protons that you might be interacting with. The phi pp, let's make sure we get this one right. So the phi pp is the correction factor that corrects for. I said there are multiple branches to the proton-proton chain. There are multiple ways it can happen. The phi pp is a correction factor on the order of unity that makes sure that all three types are being taken into account. And then your CPP is a correction factor that corrects for higher order terms that are not included in this approximation. But again, it's also on the order of unity. So phi pp and CPP are effectively really close to 1, right? But it has a really, really interesting temperature dependence. So the T sub 6 is a dimensionless way to talk about temperatures, but scaled by a million or not a million coulombs, but a million Kelvin. Okay, so if we have a T to the 6th of 1, then that would mean T to the 6th, okay, or 1 to the 6th Kelvin, because it's scaled by a million Kelvin. So a million Kelvin divided by a million Kelvin would be 1. The accepted temperature in the core of the sun is 15 million Kelvin. So it would have a factor of 15. Its T to the 6th would be 15. But it's dependent on the temperature with a negative 2/3 power by itself. But then the temperature also appears to have a square root dependence with an exponential factor. It's part of the argument of an exponential number. Okay, so this is a really, really complicated way of writing the amount of energy generation. But at the end of the day, this is in watts per kilogram. Okay, and so if you can compute what the density ought to be in your first layer, that initial layer, if you can get a pretty good guess of what it ought to be, so that your further guesses aren't too far off, then you can use the proton-proton chain to estimate what the energy generation rate ought to be from the proton-proton chain. Your CNO cycle, its expression looks like this, where its coefficient, now look at the difference between these coefficients, 0.241 and 8.67 times 10 to the 20th. Okay, so this automatically tells you that there's a very severe difference in the energy output, or at least in the way the energy is generated between these two processes. But again, it's also dependent on the density between them. X is the mass fraction of your free protons or your hydrogen nuclei, and XCNO is the mass fraction of the carbon, nitrogen, and oxygen atoms collectively as a whole. And then CNO is again that kind of higher order correction term. And again, you get your T sub 6 is a power to the negative 2/3, but now your exponential is to the negative 1/3. Your T6 dependency is to the negative 1/3 power instead of to the positive 1/2 power. Okay. And so your CNO cycle and your proton-proton chain are going to give you two very different results, right? Two very, very different results. But if you can get reasonable ideas for what these ought to be, based on the composition of, if you know what the current composition of your star is, then you can get estimates of these because you know how much carbon, nitrogen, and oxygen are in your star, and you know how much hydrogen is in your star. And that will allow you to compute the energy generation rate. And if both of these are happening, and this is really interesting because the particular types of stars that I study, Delta Scuti stars, you actually have to take both of these energy generation rates into account if you're going to do it really, really properly. But so these graphs give the results of a basic stellar model with solar parameters. So we're basically trying to model the sun using these equations, and these are the output. So the two that I find the most interesting are the temperature and the density. Okay, so the temperature starts out at 15 million Kelvin, and before you reach the end of the nuclear fission region, roughly a third of the way through the star, you've dropped a little bit more than half of your temperature, right? So you start out at 15 million Kelvin, and by the time you reach the nuclear fission / radiation zone boundary, you're already down to about 7.5. So it's roughly half. You've lost roughly half of your temperature in just a third of your radial distance outward. Then as you move through the radiative zone, you've lost nearly 90% of it, and then you lose the rest to, or once you reach the surface, right? Your density is rather interesting. It starts out extremely high, and then it's almost gone by the time you reach the edge of the nuclear fission zone, not fission zone, but fusion zone, and then it effectively dies off in the middle of your radiation zone. Your fraction of luminosity, so that would be the results of these two equations together. Again, at the exact center of the core, you're not very bright, but as you build those spherical shells, more and more light has to shine through the surface area of all of those shells. So you grow very rapidly, and you effectively hit your total luminosity at the boundary of your nuclear fission region, which makes sense because that's where your energy is actually being generated. So all of the light that you see that actually shines out the edge of the star, out of the surface of the star, has to be generated in that initial nuclear region. Okay, so you reach your total luminosity effectively at this boundary, and then you stay at that total constant brightness, right? So this is just, a pretty interesting look at the results. And even though your mass fraction of hydrogen appears right here, okay, basically in this fraction, this is for the convective zone. Once you reach the radiative zone, you'll notice this kind of plateaus out. So what this is telling you is, right at the center of the core, you're maybe a third hydrogen. Most everything else is going to be helium, but that's because when you burn hydrogen into helium, that helium sinks toward the core and it kind of pushes the hydrogen out. And so you're going to gather more helium at the very center, and then as you grow in those layers that we talked about, you're going to capture more and more hydrogen until you reach the effective total fraction of the star that is made up of hydrogen, which is in most stars right around 72% or 0.72. Okay, so this is basically telling you that you have a lot of helium, and as you move outward through the nuclear fission zone, you're still capturing more and more hydrogen to fuse into helium until you reach the point where the hydrogen fraction is effectively what we see in almost all other stellar matter, right? Okay, so symmetric and non-symmetric pulsations, right? Going back to delta Cepheid, right? Stellar pulsations can happen in what we call radial and non-radial modes. Okay, so the radial modes, or the symmetric modes, are where the star literally just breathes in and out completely spherically symmetrically, right? Non-radial modes are where that doesn't happen, okay? So I'll explain this picture a little bit more in a couple of slides, but suffice it for the moment to say, if you have a star pulsating in any of these ways, what's happening is a layer in red is going in simultaneously with a blue layer coming out. So it's almost like ripples across the surface, okay? Or in this case, if you have both latitudinal lines as well as longitudinal lines, then you can look at it either as ripples going this way or ripples going around this way. All right, but these are what are called non-radial pulsations. And both types are extremely important in studying for my purposes, they're both extremely important in the comparison between our theoretical models and what we actually see, right? But first, to kind of get a sense of what's going on, the way that the waves travel through the star for radial modes, these are acoustic waves, by the way. And so we can kind of draw an analogy with actual sound waves here on Earth. And for the radial modes, these spherically symmetric modes, we can kind of draw an analog of what's going on if we look at sound waves traveling through a pipe where one of the ends is closed. Okay, so if you look at a sound wave traveling through a pipe where one of the ends is closed, you will always have your wave die off at the edge or at the closed end, and the wave will reflect at that point. Okay, so if your initial disturbance was created out here, that wave travels through the pipe, it'll die off, hit the boundary, and reflect. Okay, where you get your wave dying off, or where we say zero amplitude, this is what we call a node. Where you get maximum displacement, this is what's known as an antinode. So the fundamental tone in a pipe is when you have one node and one antinode. Okay. The next way that a wave can exist in the pipe is if you have two nodes. And here we will have two antinodes. You will always get an antinode at the open end, by the way. Okay, so all of these waves are created such that you get increasingly more nodes, but always such that you get a perfect antinode at the open end. So I have a node at the closed end. I'll have another node somewhere in between the closed end and the open end, and then I'll have a node at the open end. So this is the second harmonic. The third harmonic is when I have three nodes, and then I'll also have three antinodes. Okay, so again, if the wave starts at the closed end, it will do this kind of thing, and when it reaches these 2 points, the displacement is zero. These are nodes, and it'll hit the edge, and it'll be reflected, and you will get perfect symmetry. Okay, so the analog for stars is such that if I have a star pulsating radially in the n equals 1 mode, it means that the pulsation amplitude grows at zero from the center, and then it grows outward, and then it just falls back inward and it goes back to zero at the center. So this is literally just going like this, right? Your n equals 2 mode is when you have two nodes between the center and the surface. But like the pipe, your surface will always be an antinode. That's why you get the largest arrows indicating expansion and contraction at the surface. That's where you get your maximum displacement. Okay, So you'll always have an antinode at the surface. So you have nodes here and here, and then you get growth from almost zero to a maximum, although the maximum is smaller here. And then it dies back down, and then you get the maximum again, and then it reflects back and goes back the other way. So this would be like in an inner region of your star, in this region of your star right here, your star is doing this, and then you have a node where it's not doing anything, and then beyond that and the surface, it's doing this. Okay, so I know it's kind of hard to visualize, but hopefully you get the idea from the pictures, right? Your material is literally kind of going like this in between the two nodes, but the amplitudes die off at the nodes, and then it's doing this toward the surface. And by the way, this is doing completely spherically symmetrically. Okay, so radial modes are denoted by their number n. Okay, so n equals 1 is your fundamental radial mode. N equals 2 is when you have two nodes. N equals 3 would be when you have three nodes. And you'll notice a couple of things. Number one, this n equals 2 mode, your material doesn't have to bounce as far between these nodes, so it shouldn't take as long. Your n equals 2 frequencies will, in general, for the same star, your n equals 2 frequencies will be higher, or your periods will be shorter than for your n equals 1. And so on as you go up in n. Okay? Your non-radial modes are defined by what we call the L and the M number. Okay? So your L number is the total number of not latitudinal, but latitudinal or longitudinal lines. Okay? So, and M is the total number of lines that go through your poles. Okay? So L is the total number of non-radial lines. M is the number of those lines that go through the pole. So if I have 5, 0, that means I have 5 total non-radial lines, but none of them go through the poles. That means these are completely latitudinal. And so again, this is a case where if I have blue, like at this pole, my pole would be moving in, and then the next layer would be moving out, and then the next layer would be moving in, the red would be moving out, the blue would be moving in, and then the red would be moving out. So you kind of get this wave going like this across the star. Okay, so that's why it's not spherically symmetric. It kind of makes it deforms the star into very weird shapes. Okay, and the I being 90 means that I'm looking at this face on. I equals 45 means that I'm looking at this a little bit obliquely, and I equals 0 means that I'm looking at it completely obliquely. All right. L equals 5, M equals 2 means that I have 5 total non-radial lines, 2 of them being polar. So I would have 2 lines. Here would be the first one, and here would be the second one, intersecting at the pole. One of them, one intersection would be up here, and the other would be hidden at the bottom. Okay, but again, the same thing applies. Anywhere that there's blue is doing the exact opposite of the red. So if the blue part is contracting, then the red part would be expanding, and the blue would be contracting, and the red would be expanding, and they would do that alternatively. So you can imagine if you had like L equals 7 and M equals 5, okay, you'd have a lot of lines, and you would start to split your the surface of your star end up into really small sections, and they would all be kind of like jiggling all at the same time. It gets really, really complicated, right? But if L and M both have the same number, then all of your lines are polar, and that's when your wave is kind of like going across your star like this. All right. So that's non-radial pulsations. So these pulsations propagate through your star as acoustic waves. Okay? So the speed of sound in a medium is given by this expression. Oh, by the way, here's that pesky pressure and density again. So here's your adiabatic constant. So your adiabatic constant basically is a way of talking about how easy it is for energy to be transported through your medium. Okay? And so, and by the way, this is not ubiquitous to stars only. Okay, this is a general expression for the sound speed in any physical medium. Okay, with a fluid medium, by the way. So if I know what the pressure is in the medium and if I know what the density is in the medium, then I can. One of the easiest things to do is to assume an ideal gas, and if I have an ideal gas, I can talk about what the how it behaves adiabatically. But so the whole idea is the goal is to measure the period. Okay, I want to know what the period is of a pulsating star because I want to use the stellar structure equations to predict the periods based on this slide, right? So I want to know the period of pulsation. So if I have a wave moving through my star, this is the speed, but I know from general considerations that time is equal to distance divided by speed. But my speed is not constant because my pressure changes throughout the entire star. My density changes throughout the entire star. For our purposes, we generally assume that the adiabatic constant is in fact constant, but this is still complicated enough because like we saw, if we come back here, this density is not like, you can't fit it with a true elementary function as a function of radius very well at all. And that means that this is a truly numeric calculation. Okay, to do this completely the right way with realistic models requires a computer, but you start right here. Your time is equal to your distance divided by your velocity, but this is a non-constant velocity. It is a function of your radius, okay? Your sound speed is going to be a function of your radius because your pressure and your density are going to change based on your radius. So what that means is I have to split that stellar model that I used. I'm going to go back to that grid of spacing from the core out to the center, and I'm going to integrate the sound speed in each of those layers, and each layer has a thickness dr, and I'm going to compute what the sound speed is in that layer, going to compute what the sound speed is in the next layer, compute what the sound speed is, sound speed. How much time does it take for sound to cross that first layer? How much time does it take to cross that second layer? And so on from the center of the star to the radius. And so that's what this integral is doing. Now, to get an idea of a general idea of what's going on here, okay, one of the best exercises to get a sense of what a star is doing is to make some very simplified assumptions. In this case, we're going to assume that our star has constant density. We know from realistic models that this is not true at all. We go from 150 grams per cubic centimeter down to almost zero. Even in the middle of the star, the density dies off extremely rapidly at the beginning, and then it becomes extremely small toward the edge of the star, or the radius of the star. Okay, but to just do something that we can actually do some back of the envelope calculations with. So we're going to assume that the density is constant. And what does that do for us? Well, density is defined as the mass per unit volume. And we can immediately then put that into our equation for hydrostatic equilibrium, the dr equation, or this equation. Okay, we can immediately put this into that. Okay, so if we arrange, well, okay, let me back up. Rho is equal to mr over 4/3 pi r cubed. So what I'm doing is I'm putting rho times 4/3 pi r cubed in for mr right here. Okay, that's the idea. And this is what we get when we do that. Negative 4/3 pi g rho squared r. So then we can plug this dp, we're not really plugging in. We're integrating this equation. Okay, we're going to integrate this equation to get what our pressure distribution as a function of radius ought to be. Okay, so if we integrate this expression from 0 to r, we set it up in an integral of this form. This is the pressure function that we get. Okay, so all this stuff is constant out front, but the real thrust is that it is negatively parabolic. R squared is the capital R, I really should say. Capital R is the surface of the sun. Okay, so negative R is a variable. So capital R squared is a constant, negative R squared is a variable. It is a parabola. This is an upside down parabola. So our pressure starts at a maximum and then dies off. Okay, or I guess from your point of view it would do this. So it would kind of resemble the temperature, the way the temperature behaves. Okay, this is not quite a upside down parabola, but you can use your imagination, especially in this region, to make it kind of look like one. Right. So this is an upside down parabola at the center of the star, and then it dies off to the edge of the star. Okay. And so, since the period is the time to complete one cycle, the full period is going to be given by twice this time integral that we had before. So this is just any generic time, but this is the time to go from, I'm sorry, it's not any generic time, it's the time to go from 0 to the surface. So this is the amount of time it takes for the sound wave to start at the center, propagate to the edge, and then come back. Okay, or this is just to go from the center to the edge. Multiplying it by 2 times that is the time that it takes to go from the center to the edge and back. So we're defining capital pi to be the period that we're looking for. This is the period that we are looking for. All right. And so it's going to be twice that integral. And when we actually plug in the expression for the sound speed, this is what we get. But we have this ratio of pressure to density. And from our previous result, okay, our pressure is 2/3 pi g rho squared times this difference of the radii. So when I divide that by the density, one of the densities just goes away. So my result is 2/3 pi g rho times the difference of the radii squared. So now I can put this into my integral, and when I integrate this, this is the result. It's constant. Okay? So this period, this derivation is giving me an estimate on a very simplified stellar model, okay? A very simplified stellar model, this is giving me an estimate of how long it'll take for the wave to start at the center and be reflected all the way back to the center after having reached the surface and coming back. Okay? And notice that really, if you assume the adiabatic constant is 5/3, which is pretty standard for most gases empirically, the only thing that is variable is your density. And it appears in the denominator of this equation. Okay? So what this is telling you is that your period is equal to some constant stuff times 1 over the square root of your period. And that's exactly what this equation, pi is equal to k over square root rho. K is just representing all the stuff in here that's constant. The square root of 3 pi over 2 gamma g. Okay? But the fundamental physics is that your period should be related to the average density of your model through this relationship. Your period is equal to some constant times the rho to the negative 1/2 is really how I should say it, to 1 over the square root of your density. Okay? So that brings us to the mean period, or the period/mean density relationship. Okay? So from the previous consideration, we've argued and we showed an explicit, albeit a simplified, but one that we could actually get results with pencil and paper, that you achieve a result where your period is proportional to 1 over the square root of your density. Okay? And some very careful considerations were done, and this equation was arrived at. And so this basically says that your pulsation period is equal to a constant Q, what we call the pulsation constant, multiplied by the density of your star scaled by the density of the sun. Okay, and these are average densities now. So this is the total average density of the sun divided by the total average density of your star in question. Okay, so Q is known as the pulsation constant, right? And each way that we were talking about that stars can pulsate, either radially or non-radially, if you're in the n equals 1 mode or the n equals 2 mode, or if you're in any of these non-radial modes or any combination of the non-radial modes, each individual specific way that your star can pulsate is going to have a unique pulsation constant attached to it. Okay, so there's going to be a unique Q, a unique Q attached to each mode, and each of those modes, each of those individual ways it can be pulsating, will have roughly the same constant. Now, it's a little unfortunate, but it's not really constant. Okay, Q is not exactly constant. It does depend a little bit on the age of the star that's in question and the stellar composition. Okay, so as you age, your composition is going to change as your hydrogen burns into helium and so on and so forth, and that affects your pressure, temperature, and density distributions, and that will slightly affect your energy generation rate, and that will affect your the way the sound waves can propagate through because your material's changing. So even though it's not exactly constant, it's still constant enough such that in general your n equals 1 radial modes for any given star that pulsation constant will effectively be about the same, and there will be very little overlap with any of the other pulsation constants for your other modes. So even though it's not strictly constant, it's constant enough. Okay? And theoretical pulsation constants have been computed for different stellar masses and ages, and then we can use those predictions to compare to observations. So once again, the whole idea is we're looking at these stellar pulsations, comparing them to these theoretical calculations. Okay, so you basically build a stellar model, run it through your stellar pulsation equations, get the predicted frequencies, compute the Q's from the overall period mean density. Once you have the frequency, you can compute the period. By the way, period and frequency are just reciprocals of each other. Okay, period is the time it takes for a cycle to complete. Frequency is the total number of cycles per unit time. So period is time per cycle. Frequency is cycles per time. Okay. So they're just reciprocals. So if you can calculate the predicted frequencies, then you can calculate the predicted periods. If you can calculate the predicted period, you can then calculate the predicted Q from this equation. So you can get what the individual pulsation constants ought to be for a given particular stellar model based on the initial guesses of its age and composition. How much hydrogen does it have? How much helium does it have? And how much heavier metals does it have? And then you just put those into these equations like a crank, let them crank out your stellar model, assuming you have the correct energy generation, and then you can put it into the linear adiabatic wave equation if you want to do a simplified radial model, or your more sophisticated non-adiabatic equations, nonlinear equations. They're much more complicated. Again, I'm not going to go into the math right now. I just want to drive home the point that you use those stellar model equations, input into the stellar pulsation equations to generate those predictions. Okay. And by the way, so coming back to some primary literature, on the relation of period to mean density for Cepheid variables, this was written all the way back in 1930. Okay, again, this was done at Harvard, and this was done no less than by Cecilia Payne. Okay, so again, the first female astronomer to get a PhD from Harvard Astrophysics, cracked the code on stellar composition, the solar composition, made significant progress on stellar pulsation. She did a lot of things. And so she doesn't give any predictive formula in this paper, other than the period ought to be related to, proportional in some way to the mean density. And the negative slope here indicates that it ought to be to the negative power. Okay, so the proportional to the mean density. If you were to put an equal sign, it would be times a constant, and the square root would be on the bottom of the fraction. Okay, exactly like I had it in the previous slide, right? And another paper from 1972, Theoretical Pulsation Constants and Cepheid Masses. This was written by J.P. Cox, an absolute giant in the field of stellar structure, stellar astrophysics, and particularly stellar pulsation. And so your Q, this is the equation that I had in my previous slide, except rearranged. So in the literature, if you look at any of these primary sources, let's blow this up so you can see it a little bit easier. So Q is equal to the pulsation period times the ratio of the star's average density to the average density of the sun. So anytime in the literature you see a circle with a dot in it, that means the quantity is in relation to the sun. Okay? So the period mean density formula given by this equation. And this is the predictive equation for the pulsation constants. This paper by Fitch in 1981 actually computes pulsation constants. Okay? So this is for L equals 0, L equals 1, L equals 2, and L equals 3. So coming back down here, that would be, well, all of these are L equals 5. But so for L equals 2, imagine just two latitudinal lines here. Okay, and so like the top of the star would be compressing and the bottom of the star would be compressing while this equatorial region would be expanding, and then as the equatorial region is compressing, the poles are expanding. Okay, that would be L equals 2, M equals 0. All right, and so in this paper, again, here's the mean or the period mean density relation in terms of having solved for Q already. And they note that the typical range for Qs are in the region or in the realm of 0.0096 to 0.067. Okay. Now, something needs to be noted that this was done in 1981. And although they were using computers, they're using very primitive computer code compared to what we have today. It was state of the art at the time, but it's very primitive compared to what we have today. But the problem with doing better than this, and this is something that's really interesting, is you have to know exactly where your star is. Like if you're going to actually look at a star empirically and you're going to observe that star, you have to know all of the properties of that star to be able to model it exactly right and then get the exact right pulsation constants by running the stellar structure code and then putting that stellar structure code into the stellar pulsation constant equations. So this set of tables is still actually fairly widely used because if you either don't have programs to do that or you don't want to spend the computational time to do that, you can look at these tables if the masses of your stars are within the masses that they're using here. So the authors of this paper computed the pulsation constants for radial modes, for the fundamental radial mode, the first harmonic. So this would be, the fundamental radial mode would be this case where the star is only expanding and contracting from the center out to the edge. What they're calling the first harmonic is the n equals 2, where some of the stars doing this and then the rest of the stars doing this, so on and so forth. Okay, so you're just adding nodes between the center and the edge as you move outward from left to right in this table. So what they've done, they're looking at specifically 3 types of mass: 1.5 solar masses, 2 solar masses, and 2.5 solar masses. So these pulsation constants were calculated specifically for delta Scuti type stars, which are exactly the type of stars that I study. And the numbers on the other side, so 21, 32, 36, 42, etc., correspond to ages. Okay, so what if I have a 1.5 solar mass star that's younger than another 1.5 solar mass star? So the 21 is younger than the 32, is younger than the 36, is younger than the 34. For the 2 mass stars, the 43 is younger than the 46, is younger than the 48. So these numbers effectively correlate with ages. Okay, and then the same thing with the 2.5 solar mass star. So if you have a star that's reasonably close to any of these masses, then you can compute the pulsation frequencies, if you can find out the average density, then you can compute the pulsation constants, and you have measured pulsation constants, you have these theoretical pulsation constants, you have a direct prediction. It took us almost 3 hours to get here, but the payoff is worth it. Okay? So, you have a direct prediction, and we can then look at these tables, look at our predicted constants, compare the two, and say, okay, how close do they agree? Right? So, let's do it. Right? So, the modern study of stellar pulsation is done largely with satellites. The TESS satellite and the Kepler. Well, Kepler is now defunct, but Kepler was running between 2009 and 2013 in its primary mission, and then it lost its pointing ability, and so then they had to change its mission directive. But Kepler initially was just pointing at one patch of sky, right? One patch of sky near Cygnus, and it did this for just years. So astronomers before these kind of space-based observatories, astronomers doing stellar pulsation and binary stars and these types of things, doing ground-based observing, you're restricted to nighttime, so there's obvious gaps in your data. And if you're doing eclipsing binary stars, if you have a long period binary, like say 40 or 50 days, and your eclipse happened during daytime for you, then you have to wait, whoever knows how long to catch the next time the eclipse happens at night, visible from your location. So it's just horrific trying to do ground-based. I shouldn't say it's horrific. A lot of people did a lot of great work and sacrificed thousands, if not millions, of man hours to do the observations and the data reduction and the calculations. I mean, incredible amount of astronomy that was done between 1910 and 1999, 2000 up through 2009. But with the advent of Kepler and Corot, with the European Space Agency and the Canadian Space Agency, and now TESS, the floodgates have just opened up. There's still a lot of work to be done from the ground, but the results just keep pouring in. And now, especially with TESS, you have literally billions of stars to sift through. Okay. You literally have billions of stars that TESS has observed. So what Kepler did is it just stared at a patch of sky until its reaction wheels failed to the point where it couldn't point, and then it just kind of orbited the Earth, and it was just looking at the galactic equator. And what TESS is doing is it's just looking at a chunk of sky, and its cameras are oriented such that it can see near the galactic pole, or not the galactic pole, but the celestial pole, down to the celestial equator. And so it just is monitoring this patch of sky for 28 days, switches 28 days, 28 days, and it does 12 sectors in the 12 sectors of 28 days in the northern hemisphere, and then switches down to the southern hemisphere. So it basically gives you an entire view of the sky every 2 years. Okay. And at 28 days at a whack, this is a ton of data, right? This is an absolutely ton of data. So what we're going to do, we're going to do this in real time. Okay. We're actually going to do the science now. The study case of YY Boo. So YY Boo is an eclipsing binary. And so the light curve is going to resemble this, but it's going to have this superimposed on top of it, except with the exception that it's going to be a lot more sinusoidal. So as you move down the instability strip, you increase in density, and you decrease in the total amount of displacement that your oscillations have, and you increase in frequency. And so what that means is that your oscillations are far more purely sinusoidal or combinations of sinusoids than your like really weirdly shaped light curves where they grow rapidly and then decay over a much longer time. So we're looking for sinusoidal signatures. Okay. So here are the steps. What we're going to do is we're going to get some data. I'm going to show you guys how to do this in real time. We're going to get some data, and we're going to remove the binary signature. Now, I do it by polynomial fitting. I'm going to do it by polynomial fitting for the purposes of this video, because modeling the binary system is very, very time intensive, and it's an iterative process. So you basically have an initial guess, you let the program go through, and then based on the output of the program, you make updated guesses, and you're trying to get the guesses to be better and better and better each time. It's really, really useful if you actually want to solve for all the parameters in a binary system. So for example, if you actually had spectroscopy with radial velocity data and you had photometry with time and light data or a light curve, then you can combine these data, and it's much, much, much easier to then get an exact, or at least an estimation for the exact parameters of the solution, including the masses of both stars, the radii of both stars, and the temperatures of both stars. And if you know the radii and the temperature, you can get the luminosities. So spectroscopy combined with photometry, if you're actually going to use sophisticated binary modeling software, you can actually determine the parameters of the stars as well as the parameters of the orbit. So it's really, really useful, but it's really, really time intensive. And for our purposes, we don't need to do that because YY-Boo has already been solved. So, for example, what we're doing is we're going to pull YY-Boo, its data, which is actually right here. So the orbital period is 3.933 days. The pulsation period is 0.06 days. And let's actually do a quick calculation. There are 24 hours in a day. There are 1,440 minutes in a day. So if I multiply 0.06128 by 1440, this is every 88 minutes. Okay, so just shy of an hour and a half. So the pulsation period is just shy of an hour and a half. All right. So we're not going to take this for granted. We're actually going to measure this. I'm going to show you guys how to measure this. But here's the interesting thing. This has already been solved spectroscopically. So we already have an estimator of the mass and the radius of the pulsating component in the system. Okay. So we're going to gather the data on this system from data from the TESS satellite. Oh, by the way, TESS stands for Transiting Exoplanet Survey Satellite. So this satellite's main mission is to hunt for exoplanets. But again, because it's just looking at regions of the sky, all of the stars that it can see are fair game for people to analyze. So you can go in and look at any particular star you want, generate a light curve, and see if there's anything interesting. You can do this as a citizen scientist. Very cool. So there will be no shortage of data for people to analyze for decades to come, quite frankly. So we're going to get the data, and I'm going to remove the binary signature by polynomial fitting. Then we're going to use Fourier transform routines to actually extract what the frequencies are. So Fourier transform routines basically take your time time and brightness data and transform them into frequency data, okay, or into the frequency regime, all right? And then from that, we're going to compute the pulsation constants for our data, and then we're going to see if that matches any of the pulsation constants from our predictive table. And why I chose YY Boo was measured to have a mass, at least to within the precision that the authors could get it in, of 2 solar masses, which is an exact value from these tables. So there ought to be, if these tables, in other words, were prepared from correct predictions, we ought to be able to match. Okay, we ought to be able to match. And by the way, I'm not sure if I stressed this enough, and it's worth stressing it again. The authors of this particular paper, okay, this paper is completely theoretical up to this point. They do some empirical work later in the paper. They do some comparison of actual data with these tables and with some other formula they have after these tables. But these tables are computed from theoretical stellar models. Okay, so these are computed from these equations, complete with these energy generation terms. Okay, so these are theoretical models created from theoretical stellar structures that were then put into the stellar pulsation equations to get the predicted periods, and then the pulsation constants computed from the mean or the period mean density relation. Okay, so that's what we're going to do. We're going to take our predicted, or not our predicted, but we're going to take our measured pulsation constant and see if it matches a predicted pulsation constant, particularly if it matches one of the 2 solar mass values. Okay. Oh, by the way, I didn't really stress this enough. So this table is for your radial modes. This is for the L equals 1. So if I have 1 latitudinal or longitudinal line, this is for 2 latitudinal/longitudinal lines, and this is for 3 latitudinal/longitudinal lines. Okay. So if there's a pulsation mode that matches very closely one of these values within the mass range that we're looking for, then that's a really good indication that the star is pulsating in that particular mode. Okay. Okay. So let's do it. We'll talk about this one here in just a minute, but so let's look at YY Boo. So the Simbad database is the repository Bible of astronomical information. Okay, so if you want to know an object's coordinates, its spectral type, if the spectral type is known, its trigonometric parallax angle, if that's known, its absolute, or not absolute, but apparent magnitude in a given waveband, all sorts of things, as well as all of the catalogs it appears in, the Simbad database is the place to go. So we're going to look at YY Boo. All right. But YY Boo, TIC stands for Test Input Catalog. So if you have a tick number, this means that the object is included in TESS's initial input catalog. Okay. And so it has an initial TESS input catalog number. And this is important because if you want to search for the data through NASA, TESS is becoming so ubiquitous that it's almost easier to search for it by TESS number than anything else. And I'll show you why here in a minute. So if I actually go Actually, let's close that out. If I actually go to the NASA website, the MAST archive, this is where you can download NASA data, right? We're going to enter a target, and I've already got it in there, but I want to enter in the tick number for YY-Boo. And the reason that I would rather enter in the tick number, the tick and the number, rather than just enter in YY-Boo into the search area, I could absolutely enter in YY-Boo, but it will give me the tick number as the output. And so if I don't know the tick number ahead of time, then I don't know what I'm looking at. So we're going to hit search, even though it's already done it. But just to show you what it looks like, sometimes it can take a minute. So what it's doing is the system is basically taking the input target that you put in, finding its coordinates, centering it on a picture, and then looking for all other known targets within a certain specified range. Okay. And that's what all of this information is. So you'll notice that it has a wide variety of things here, but our tick number is 1165.02572, and that correlates with these target names right here. Okay. So as I said, TESS is observing by sectors. So each 28-day increment is a sector, and then it moves and to the next sector, the next sector, the next sector, and so on for 12 sectors in the northern hemisphere, 12 sectors in the southern hemisphere. So let's just look at this line right here. Okay. If we scroll over here, you'll notice a number of things. So here gives the data file name or the observation ID. And so the first stuff, the tests and then all of this stuff, correlates with the date. Okay. This correlates with the sector. And then there's some other naming format stuff, gibberish at the end, that's not really relevant for what we need to know. Okay. But for our purposes, most importantly, is knowing what the sector is and that we have the right target. We can then also see at what cadence the exposure length was. So this was these data were taken every 120 seconds. Not every test target was taken at 120 seconds, but for delta Scuti type pulsation analysis, it's very, very good. It's very important because delta Scuti pulsation periods are on the average of about 30 minutes up to about 8 hours. So if I have data every 2 minutes, then I'm going to be able to capture all of the pulsation periods that could be running through my data with really high precision. And the other good thing is here, you'll notice that I have data available in sector 14, sector 23, sector 24, sector 50, 51, 77, 78. I have several sectors here, so I could even do a long time span analysis and see if any pulsation modes appear in later data that didn't appear earlier, or die off and don't appear in later data that were apparent in earlier data. We'll see in just a minute that that's probably not likely for this particular target, and I'll show you why. So once you've inspected what sectors you're looking at and what the exposure lengths are, you can come back over here, and the data that have this visualize icon, you can click on it. So let's click on this one. So this is column 12, or row 12 rather. Row 12 is sector 50, and it was taken at every 120 seconds. And if I click on this, this is going to take me to an interactive light curve. And so I want you to compare what you're seeing here with what we saw here. Okay? More or less constant, a really deep dip, more or less constant, a really shallow dip, deep dip, shallow dip. Even though the constant stuff isn't really constant, you get these nice humps. You get the really deep and really shallow eclipses very well. So this is your primary eclipse. This is your secondary eclipse. Primary eclipse, secondary eclipse, primary eclipse, so on and so forth. If I zoom in, now this is a classic picture of a Delta Scuti star in a binary system. If I zoom in here, you just see this nice sine wave running through here. This is just gorgeous. This is beautiful. Okay, so what we want to do is we want to obtain the data on this target. I want to polynomial fit the data to remove the eclipsing signal and flatten the data out, run it through a Fourier transform routine to extract the frequency or frequencies. And because we have the mass of the star in terms of the solar mass and the radius of the star in terms of solar radius, that we can then compute the pulsation constant and see if it matches something in the table, right? So, I could, at this point, hit this download button, and I can download the data directly from the NASA website. It actually takes a little bit of extra prep to do that, to extract the data and get it to a point where you can actually work with it. So when it's available, I actually prefer to download data from the TESS Eclipsing Binary Catalog. This doesn't have all of the targets that would be of interest to me, but it has a lot of them. And in fact, it has WBOO, or not WBOO, but YYBOO. Remember that our tick number was 1165-02572, right? 1165-02572. And that is our tick number here. So this is all of the data of, well, this is a sample of the data. This is all of the data available to download from the TESS Eclipsing Binary Catalog. And I really, really like the data from here because they already have basically processed it for you. And so all you have to do is click on this LC button, and you just get columns of data. This first column of data is times, so these are the timestamp of each measurement. This is the phase, where each measurement is in the phase of the cycle, running from 0 to 2 pi. And this is the flux or the brightness of the measurements, and this is the brightness error. And notice, okay, so these have all been normalized so that the average is 0. The average of the total brightness is 0. Or not 0, but 1. So the average flux would be 1. And the average uncertainty is about 4 times 10 to the negative 3, or 4 thousandths. Okay? So our uncertainties on the fluxes are incredibly sharp. If you were to do a ground-based observation, your flux errors are typically going to be on the order of 1% or so. This is well under a order of magnitude below that. Okay, so the space-based photometry precision is amazing. Okay, so what you can do is you can copy and paste the data. Scroll all the way down to the bottom, hit Shift, and you can highlight everything. You can copy and paste it into a Word document. I already did that earlier, okay? And I saved the data in a file called YYBoo. And so what I also have done is I've written a Python program that does the polynomial fitting for me. Okay, so the idea of what I want to do here, by the way, just to make this explicitly clear, the idea of what I want to do here is I want to basically take this data and flatten it out so that I have a very flat light curve where everything is flat except for the oscillations. That makes it easier for the Fourier transform program to extract the correct frequencies. Okay, so I'm basically wanting to model this data with a chain of polynomials, subtract that fit out, and that flattens the data except for the pulsations. So that is what my Python program here is going to do. And notice that I've got my text file named YYBoo. And the code is kind of clumsy. I'm not a native programmer. I basically am teaching myself all of the Python programming that I need. But the program works, okay? And we'll see what's going on here if I hit go. So, where do we have a value error? New elements have 3. Oh, I'm going to have to troubleshoot this error. Hang on. Okay, debugged. I just had to add a column name in the data frame for the output. But in any case, okay. So what the code is going to do, right? If I'll break it down as I hit the button here. So I guess I really should have stated here first. Oh, I accidentally clicked out of the. I closed down the Eclipsing Binary Catalog. So it lists which sectors it has available, which is really, really helpful, but it doesn't have all of the latest sectors, right? So notice that it only goes up through sector 51, whereas the masked archive goes up through sector 78. So you have 2 more sectors available to you here as opposed to here. But with this particular target, it doesn't really matter, and I'll show you why. This is absolutely beautiful. Okay, so what the code does is it takes it displays the raw light curve, and you'll notice that there's gaps. This is where either the data was too low quality to be usable, or it was when the telescope was downloading data to Earth, downlinking to Earth, and dumping data down before collecting more. Okay, so it does that once a month. It does that once a sector. But so this is just a very repeating pattern, right? So you get your primary eclipse, secondary eclipse, primary eclipse, secondary eclipse. The second panel is all of that data phased onto one cycle of eclipse. So it's like if I start here and go from here to here and then fold that next cycle and all the subsequent cycles onto that first sequence. Okay, so you're just folding everything onto that first sequence. And that is the data that I polynomial fit. And then the bottom panel is after. So The red lines represent the polynomial fits of the phased or folded data. And the bottom panel represents after I subtract the red models from the actual data and then reorganize them by time. So resort them by time. So you'll notice the middle two panels have the same x-axis. Your phases go from 0 to 1 or from 0 to 2 pi, depending on how you handle it. But in our cases, from 0 to 1. And the top and bottom panel have the same x-axes, and these are times. Okay. And these are not years, so this isn't 1930 and 1940, but these are days with respect to some specified initial starting day. Okay. So these are not years, but these are days with respect to some initial starting day. But so the whole idea, the whole point here is notice how clean that is. That's as clean a sine curve as you will find in stellar astronomy. Okay. That is as clean a sine curve as you will find in stellar astronomy. And the cleanliness of that curve indicates that we might only be dealing with one frequency. Okay. If you had multiple frequencies, then you would be expecting something like this. Okay. If we go here, I know that this particular star is a multimodal Delta Scuti star because it was one I published on, KIC 106-84673, Delta Scuti variable, and its tick number is here. And so if we search that in the MAST archive, what do we come up with here? By the way, thank you guys for hanging with me, but I hope that we haven't even gotten to the punchline yet, but I hope that you're finding the process, kind of each stepping stone. What we know here at the top, the stellar pulsation stuff, the stellar modeling, depends on the rungs of information below it, right? So all of this is like a staircase of evidence, and the upper rungs depend on the lower rungs. And without the lower rungs being true, the upper rungs mean nothing. And if the upper rungs are wrong, then that can spell disaster for a number of things, right? And so we have sector 14 and 15 that were available in the 120-second cadence for this multimodal Delta Scuti star. And this is what the light curve would look like if there were multiple frequencies running through the data. Okay, so it's sometimes easier to show the line, and then we'll come back here and look at a small section of this. So you can see that the amplitude of the dominant sinusoid is not constant. Okay, and so that tells you that there's multiple frequencies running through here. But this data is extremely constant. Extremely constant. And, okay, so now what my program does is it outputs this flattened data into a file, a new file, labeled whatever your original file was, in my case YYBoo, and now it's generated a file called YYBoo/fit. So this is YYBoo's data fit with the polynomial chains, subtracted out and flattened. And now I can put this file into a frequency search program. Okay. So a quick note about frequency search programs. Your classic Fourier transform, a classic periodogram would be given by this algorithm right here. So this paper, the Lomskargel paper, was submitted by Jeffrey Skargel in 1982, and he and Lohm both wrote and improved upon an algorithm for the classical Fourier transform to account for uneven data collection. So in a classic Fourier transform, your TJs, or your each time increment, each time collection, is ideally uniform. Your data is evenly spaced, but in astronomy, that doesn't happen. Again, if you're a ground-based astronomer, you're naturally going to have breaks from day to day or night to night, or from month to month or season to season. And space-based, even though, this test data is really, really clean, you still have a break here, you have a large break here, you have a large break here. So there's no such thing as completely evenly spaced data in astronomy. You can have subsections that might be evenly spaced. So for example, if you only wanted to use, for example, this set of data right here, that would be more or less evenly spaced. There's not a break in there. But in general, if you want to use all of the data available, you're going to have breaks. So they wrote a new program, or a new algorithm, a new definition of the periodogram, that allows for corrections to be put in that allow for the extra weights, or the breaks, effectively. They wait for the breaks, effectively, is what I'm trying to say. Okay, so you have your classic sine and cosine curves, but with these extra weighting factors. Okay, and as they say, the form is significantly changed, but the actual computation time is not really increased that much, and the improvement is measurable, but it's not like out of this world better. And this video, we really don't have time because we're already pushing 3.5 hours. So if you've stuck with me this far, holy cow, we're minutes away from the punchline. So please, if you are thinking of clicking away, if you do so, come back, okay, at some later time, because we're minutes from the punchline. So as a matter of fact, I'll shut up about this. All I'm going to say is that this is the algorithm we're going to use, the Lomskargel routine, to calculate our Fourier transform. And Python, the astrophysics community, has built a package called AstroPy that has a number of useful tools in it, and the Lomskargel frequency spectrum routine being one of them, right? So all you have to do is load in the YYBoo fit, and actually I think I need to adjust these, since let's check YYBoo fit for just a quick second. Okay. No. I don't. I was worried that since I had the data frame program issue in the last program, I needed to include 4 columns here, but I only zip and export the times, fluxes, and errors here. So this program imports the times, fluxes, and errors for the flattened data, and then frequency searches the flattened data. And what I would typically do, because delta Scuti periods are typically from, uh, 30 minutes up through 8 hours. In terms of frequencies, that's roughly 3.3 cycles per day up to 100 cycles per day. So I'm going to frequency search between 3.3 hertz, or not a hertz because that's cycles per second, but cycles per day up to 100 cycles per day with this data. And I need to close this out if I want my new graph to appear. And here we go, right? You'll notice, okay, so here's the flattened data, and there's a single spike. Here's a secondary spike, but we get a single spike right here. And as a matter of fact, let's actually zoom in here just real quick. I'm going to claim that this spike isn't real, and I'll explain why here in just a minute. But if we zoom in here, okay, we can clearly see that this spike is between 16 and 16.5. But so my frequency search range was very, very wide. So if I zoom on this even more, you can already start to see a little bit the it's hard to see there, but you can start to see the individual gradation between the periods that were used, right? You can start to see where the shoulders are in the individual frequency regimes, or the individual frequency spacings that were used to search. So to get a refined idea, we know that it is between... oh, by the way, the program also spits out the maximum period, or the frequency associated with the maximum power. So this 16.31828, okay, 16.31828. That is the frequency. The rest of these numbers are really meaningless. You can get wrapped up in sig fig issues, but for our purposes, 16.31828 is perfectly fine. 16.31828. I'm going to refine the frequency regime to be between 10 and 20, and let's see what that does. Okay, so here 16.31834. Now, I don't have written in here a routine to determine the uncertainty, but you can put one in based on statistical calculations. Okay, you could absolutely put one in, and in fact, you really should. But for our purposes, what we're after is that frequency peak right there. So for all intents and purposes, we can make a frequency estimation of 16.31835. Okay, so 16.31835. So I'm going to put that in here, 16.31835. So our frequency, and remember I said that our period is the reciprocal of that. So my pulsation period, I can compute to equal 1 divided by my frequency, and I get 0.061281 days. And if we come back here to our reference that we are working from, we can see YY boo. Oh gosh, 0.061281, 0.061281. We hit this on the head with a comparison with the literature that we're drawing this from. So we can be very confident that we found the same pulsation period that whoever did this earlier. In this case, it would have been the references in the table, 17 and 41. It would have been Hampsh et al. Or Svetnikov and Kuznetsova. I don't remember which reference actually had the published period in it, but we're getting the exact same period that they got. Okay, so our pulsation period we can then use to calculate the pulsation constant. So the pulsation constant, the formula again is equal to the period times. So if we come back a slide, we need to come back here. Nope, come back here. The pulsation period is inversely related to the density of the star in question, scaled by the density of the sun. But if I rearrange that equation for Q, then the fraction flips. So Q is proportional to the density of the star in question and inversely proportional to the density of the sun. So we get this. The mathematical convenience is if it's scaled by the sun and I'm using parameters measured in solar units, then the density of the sun is just one solar density unit, if you will. What that means is now all I have to do is I can get rid of the rho sun. It scales to 1. And now I just have to compute the density in terms of the solar units of the star. Okay? But that means density is mass over volume, and volume is just dependent on the cube of the radius. The 4 pi cubed, or the 4/3 pi stuff appears in both the numerator and the denominator here. So the 4/3 pi business cancels out, and I'm just left with the ratios of the masses and the radii cubed. And since the solar values are set to 1s, by definition, a solar radius is 1 solar radius, I'm just left with the mass in solar units divided by the radius in solar units of my target star. So that's what we have, okay? I've taken the period, so this is my capital pi times the square root of my mass divided by my radius cubed, and my predicted pulsation constant, whoops, I didn't want to do that. Let's come back here. My predicted pulsation constant is 0.033. 0.033091. So let's just call it 0.0339. Let's limit this to 4 sig figs. Whoops, not 4 sig figs, but 4 sig figs. I wanted 4 sig figs, not 4 decimal places. Okay, so 0.03309. Q measured. So here's where we go to the table. Here's where we go to those tables. Okay, Fitch has 2 solar mass values. Now, notice that these are all multiplied by 100, so I need to divide these by 100 to get the actual predicted pulsation constant. And so we have the radial modes for our 2 solar mass. These are all the radial modes, the fundamental, the first harmonic, second harmonic, so on. 2 solar masses predicted for the L equals 1 modes, the fundamental mode, and then all of the harmonics. Same thing with the L equals 2 modes. I would look at the 2 solar mass values and see if they match anything here. and then the two solar mass, and see if they match anything in the L=3 modes. So if I divide these numbers by 100, we'll see that this would be like this value right here would be 0.0. If I move the decimal 2 places, it would be 0.03283, right? 0.03283. This one would be 0.03277, and so on. So I'm looking for a value corresponding to the two solar mass values that's closest to this 0.03309 value. And it turns out that if you go through the table, okay, so this would be 0.036s. These are 0.032s. These are 0.034s. Here's 0.33s and 0.34s. But the actual absolutely closest value happens to be this one right here, 0.03283. So we're going to claim that the closest matching measured pulsation constant value is 0.03283. Now these don't match exactly, okay? They don't match exactly, but notice how well they do match. Roughly 0.8% away from each other. So what this means, what does this mean for Kent's argument? What does this mean for Kent Hovind's argument? If stars got their energy from gravitational collapse, then it means that this is just an absolutely serious coincidence that we can compute predicted pulsation constants for stars of a given mass and then measure extremely similar pulsation constants for a star of the same mass, at least to within the measured precision, the allowed precision from the measured spectroscopy. To the point where the difference between these two values is the same thing as the difference between $1,000 and $999.92. If this is $1,000 as a prediction, as a finding, let's do it this way. If this was $1,000 as your prediction, this would be like finding $1,000.08 or $999.92. That's an extreme coincidence if our understanding of stellar structure is not correct. That would mean if stars are still actually operating, particularly the sun, if the sun were operating on gravitational collapse and all other stars on the main sequence were still operating under gravitational contraction, that would mean that all of the equations, both the stellar structure equations and the stellar pulsation equations that the stellar structure equations are inputs for, would be bogus, and somehow we miraculously were able to compute these predicted pulsation constants and find one almost with an exact match for the same mass of star. And by the way, not only that, just from experience, I could tell you that it is quite likely, not that one, but this one, I can tell you from experience that this is quite likely the fundamental mode just by looking at it. That takes some practice to get to, okay? That takes some practice to get to, but I can tell you that this is quite likely the fundamental mode based on its overall frequency and amplitudes. Because remember, the fundamental radial mode is going to have the lowest frequency per given star, or one of the lower frequencies anyway, and one of the highest amplitudes. So the fact that there aren't a ton of modes running through here, the fact that it's very well defined, and the fact that the amplitude is very well defined, that reeks of at least the fundamental or the first radial harmonic. Okay, so automatically, before going anywhere else, I would absolutely go to this column or this column and look. And lo and behold, we get a value that is within 2%. Now, something that's really interesting is this one right here. That one almost matches exactly. Okay, that's a coincidence. It is a coincidence that we get a pulsation constant for a different mass that is actually closer than for the mass that we're interested in. That's a coincidence. What would actually happen, much more likely than not, is that if we had multiple modes running through here and we actually could extract the frequencies of those modes and get the pulsation constants, we would see that the overall agreement for the two solar mass pulsation constant predictions agreed better. But you might find individual pulsation constants that are closer to values from the other masses. But again, also remember, okay, that these pulsation constants are not absolute. These pulsation constants were computed with primitive code relative to what we have today. It's just that today's computer code requires a lot more computational power and a little bit more guesswork and or working with grids to find the right stellar model for your specific star at its specific stage. The pulsation constants here were also computed with some simplifying assumptions that are not in the modern stellar pulsation codes. So like adiabatic wave equations as opposed to incorporating non-adiabatic linear versus nonlinear. And as soon as you go nonlinear, then your computing power goes up the wazoo. So if you're writing this back in 1981 on primitive computers compared to what we had today, primitive languages compared to what we had today, it makes a lot of sense that you're going to try and simplify things as much as possible. So, presented with this, the fact that we can predict correct pulsation constants for observed and compare those predicted pulsation constants to observed pulsation constants and get percent errors to within less than 1%, either means that this is a coincidence of extreme proportions, or we're very much so on the right track. And even if these tables were computed with some simplifying assumptions, enough of the viable physics is included to at least capture more than just the general state of the phenomena, but the biggest pieces of the phenomena. Incorporating the more sophisticated models is only going to further refine them, not fundamentally change them. Okay. Now, why is this important? The discrepancy between these is actually very interesting because it means if we actually can get more, spectroscopy and photometric data on these in different color bands, if we can get those masses refined even further, if we can do better than just say it's two solar masses, if we can like 2.1, 2.15, 1.8, 1.85, if we can actually start to narrow it down a little bit better, then we could go to the stellar modeling codes of today, build up a few stellar models, a few given masses around that, determined mass, and see if it matches any better, right? See if we can get predicted pulsation constants that are any better. And then we can find the model that agrees the absolute most, find its discrepancy, find its percent error between the measured and the calculated, and then we can start to go, okay, what physics are we still missing? Stellar pulsation is the way we get into the interiors of the stars, because these predicted pulsation constants come straight from the stellar pulsation calculations, which are built on the stellar structure equations. You tweak the stellar structure, it tweaks the output of the stellar pulsations, the stellar pulsation equations, and therefore the Q predictions. So this is how we start to figure out what's going on inside stars. We've done this whole thing is called astroseismology. We've done this for the sun to incredible precision. That's why we're incredibly confident with this output model of the sun. Okay? We are incredibly confident. But it still is an open question. Okay? Exactly what fraction of the energy generation should be proton-proton chain? What fraction should be CNO cycle? And I will 0.01% credit to Kent Hovind. If you want to do a time evolution of a star, you do have to include gravitational contraction. And that actually contributes time dependency into the stellar structure equations, so that you build your stellar structure from the center of the star out. And then when you include the gravitational contraction in that, it automatically has a built-in time dependency that then allows you to compute the next time interval from the center of the star outward, next time interval, and you get to see the evolution of the star. Now, I'm actually simplifying how the stellar structure codes actually work. The most sophisticated models of today don't just start at the center and integrate outward toward the red or the edge of the star, the radius of the star. What most of the sophisticated programs today do is they actually go both ways and find a point in the middle that's a matching point, and they make sure that the integration from both directions matches at that point. And it's because both edges, the center and the radius, the edge of the star, the surface of the star, I really should say, have unique boundary conditions. And it hurts your numerical modeling if you start with the boundary conditions at the center and try to integrate outward, and your surface boundary conditions start to become numerically unstable. If you start at the surface of the star and go inward, then your boundary conditions at the center cause your code, cause the numbers to start to become unstable. So if you go inward and outward at the same time and find a spot in the middle that both directions can agree on, then you're ready for the next step in your evolution code. Okay. So, yes, gravitational contraction does play a role over the long term of the life cycle, but the vast majority of your energy generation has got to be nuclear fusion. Or else, this would be a phenomenal coincidence. I mean, a phenomenal coincidence. It would be one of the biggest coincidences in science. Okay. Now, and by the way, this is just one line of evidence. This is not even the comprehensive set of evidence, but it's a line of evidence. And we're running on 4 hours in this video now, but if you've hung with me or have been able to watch the video in chunks, kudos to you. I hope you found this enlightening. The punchline is absolutely worth it. The fact that we observe pulsation constants in stars and have readily available predictions for those pulsation constants that agree to within a percent, we can then use to refine our models to figure out where in the stellar pulsation, not the stellar pulsation, but the stellar structure piece of it is lacking, and try to tweak that to then be able to refine even further. This is not going to be overturning what we know about the interiors of stars, but adding to it. I would absolutely go so far as to say the general overall picture we have is pretty good, if not really good, if not really good. We are just now in the nitty-gritty of looking at the details, right? The details of the details. And that's exactly what this number is indicating to us. It's not perfect, but we're very much so on the right track. And even if you're using a simplified picture in your stellar structure models and your stellar pulsation models, you can still capture enough of the essential physics to do a really good job and make some really firm connections between theory and prediction. And just to kind of drive this point home, okay, even in current papers, okay, so this particular paper, a grid of 200,000 models of young Delta Scuti stars using the MESA and Gaia software. These are the premier stellar modeling and pulsation modeling softwares. And this, a year old, right? So this was published in September of 2023. And they have a statement here in their paper when talking about compositions and nuclear reactions. Let's see, where do we want to use? Okay, so the code includes both proton-proton chain and CNO cycle reaction rates in the nuclear reaction network. And you can either use one or the other or both. And what they note, if you just use either or, you don't get very good results. But if you use both the hot CNO and the proton-proton chain extra packages that incorporate even nonlinear effects and some of those correction factors, they incorporate these correction factors to a higher degree, then you get much, much better performance. Okay, so it's still an open question exactly what percentage of the proton-proton chain, what exactly the percentage of CNO. We know pretty good, but we're still working out exactly how it, and it's going to be different from star to star, and that's actually part of the challenge and the fun of stellar astronomy right now, because there's still a lot to learn. We're refining our models. The space-based photometry is amazing. There's just so much work to be done, no shortage of it, but we're still able to actually get concrete results, publishable results, and testable results. And I think that this is what annoys me so much about Kent's position, is he acts in a lot of these videos like astronomy can't really be tested, because, yes, we are looking back in time, okay, but you can still test things. And it doesn't seem like he wants to be able to accept that. And he's really picky and choosy about what he includes in his version of science. All of that is for a future video. We're coming up on 4 hours. If you have stuck with me, by golly, kudos to you. Drop a like, drop a comment, let me know what you thought. I really hope that actually seeing the science done in real time is useful. And so if that is useful to you, fantastic. Hopefully it inspires you. If nothing else, hopefully it helps make you think, learn how it's done, and that we can do it. That's the point, that we can do it, and that we are doing it, and that we're not just taking shots in the dark about this theory or that theory. When astronomers talk about what's going on in the interior of the sun or the interiors of other stars, we're not speaking from a place of ignorance. We're speaking from a place where atomic physicists have toiled and toiled and toiled to give us these two equations for the energy generation rate. And they've also toiled to give us the energy generation rate once you're off the main sequence and you're burning helium now. When you're burning helium, you're not doing these two things to a large degree anymore. Now you have to know how the helium chain works. There's a host of atomic physics in the interiors of stars. And the atomic physicists have been gracious enough to share their field with us. And we astronomers, hopefully, are gracious enough to let our results that are useful to other fields, and those other fields are gracious enough when their information is useful to us. And so science advances by these little tiny incremental steps, each little tiny incremental prediction that can be refuted or affirmed. I hesitate to say proven. We do not say proven. You can disprove with a test, a well-done test, a verified test, but you cannot prove, but you can affirm. So that's why I would say that each of these layers, the stellar parallax, and figuring out how bright stars actually are once we know their distance, that allows us to talk about the Hertzsprung-Russell diagram. How are stars distributed based on their spectral type? Then once you have the HR diagram figured out and you realize it's not a migration across the HR diagram from bright stars to dim stars, but that it's a migration from where you are on the main sequence to whether you become a giant, a supergiant, whether your fate is ultimately a black hole or a neutron star or a white dwarf or a helium ball, then all of a sudden the opacity issue comes up and you go, wait a minute. For stars that are going to be in this strip, they should have energy dammed up in their outer layers where the opacity can be written down like that power law. And you should see layers expanding and contracting if that's true. And that's exactly what we saw. And we find that in several different classes of pulsation variable. There are well over a dozen class of pulsation variable at this point. My specialty is Delta Scuti stars. And then you can say, but wait a minute. If stellar pulsation is happening, it has to be dependent on stellar structure. So then you have to figure out the stellar structure, put it into the pulsation code, see what the pulsation predictions are, compare those to known results. And this is why the eclipsing binary system is extremely fortuitous, because it gives us an external way to have the masses and radii handed to us. This gives a direct way to test these pulsation constant predictions. So again, either all of this is built on a house of cards, that it just happens to be a coincidence that it all fits, or we actually really do have a good working picture about stellar structure, the distances to stars, the lifetime and lifespan of stars, and how stars are going to evolve across the HR diagram. Okay, so when people like Kent spout out one of Kent's strengths, and I'll wrap up with this thought. One of Kent's strengths is that he knows how to Gish Gallop really, really well. And this was a pseudo Gish Gallop. Notice that he hardly gave his debater any time to respond. Hugh Ross is a PhD astronomer. I have the benefit of stewing on the debate, having listened to clips of it multiple times, sleep on it, think on it while I'm doing the dishes or folding laundry or whatever. I have the ability and the advantage of looking at this from the outside. If Hugh had a few moments to digest what Kent was saying in that instance where he talked about gravitational contraction, he absolutely would have spoken up and said, wait a minute, no. We know relatively well to an extraordinary amount of precision that it is not gravitational contraction, at least not gravitational contraction alone. We have really good evidence that the bulk of energy generation on the main sequence is actually due to nuclear fusion. And there are a few other points in the debate where that could have happened as well. But that's one of Kent's strengths, is that he will Gish Gallop over these points. He will almost Gish Gallop himself. He will just bring up point after point, and he doesn't even let his opponent respond. Not that they even try to respond, but he gallops to the next point before they can even respond. And, you notice how fast he talks. He's like, well, it could be gravitational collapse, or it could be nuclear fusion. And didn't even give Hugh, he didn't even say, as an astronomer, what do you think? Doesn't even say, as an astronomer, what do you think? He just says, we have two theories, as if he has done the research. He's done enough research to know that we had two theories, and that we actually still incorporate one marginally into a static model. We do incorporate into evolution models. I have to be very careful with that word because it means something to Kent that it does not mean to an astronomer. Stellar evolution as your star ages. We do include it in those, but just a snapshot of where your star is right now, you don't need gravitational collapse. You don't need gravitational contraction as an energy mechanism. And in fact, this shows you that to a really, really, really good degree, you don't need it. A really good degree. So I hope you enjoyed seeing science in real time. I hope you enjoyed the conclusion here. Hit that like, subscribe button. I don't get to post as regularly as I would like to right now because I am working fervently on my PhD. But this is the kind of work that I'm doing, by the way. So it's fun. It's applicable. We're making progress on contributing to not only figuring out how stars are pulsating, but where we're deficient in our stellar models, which is really cool. If all of this is a house of cards, and by the way, it doesn't even go into, the actual collection with the telescopes. the optical physics that goes into data collection, the quantum physics that goes into the data collection with modern sensors, and so forth. So like every branch of physics, mechanics, thermodynamics, electrodynamics, optics, quantum mechanics, all of it is wrapped up into either the data collection or in the physics of the stars itself. So if we didn't know to a really good degree, then this would be the biggest coincidence, period, right? Maybe not the biggest coincidence, but it would be a damn large coincidence. Okay. So with that, I'm going to sign off. It's 8:21 a.m. Good night. Have a good day. And I hope you found this helpful. We will talk to you later.